I said, gone. Yeah. So let's take a look here. So I started to make I think I should stop video. Hello.
You want them to see this?
Yeah,
Okay.
but I will showing a slide first, but you can see me first.
Whichever you want. If you want slides first, we can.
No, no, I should start,
Okay.
then go to slides,
Yeah.
no? Okay. Not many people. Yeah. Electric guys are not very comfortable. Can they hear us?
Yeah.
Right? Good. Good. There are not many schools are teaching advanced electric drives. That's really the mission. So, can they hear me from this here?
They should be hearing you.
But through here.
Yeah.
Okay. But you can hear, I mean, you're logged in,
Yes.
so you can hear it through headphones, right?
Yeah.
Okay, we should start. Yeah, good morning, everybody. So welcome to this course on vector control of electric drives. And again, it's a 3-day short course taught by Siddharth Raju and myself. And so I'd like to show you a few slides to put the context in which we teach this course. And so let's start with that. So I have to go to the slides. So I go to share, and then go to the slides would be right here. Right here. So if I go to the slide view, wait a minute.
Yeah.
Seems to have some slides that we had deleted. So let me minimize this here.
You can stop.
Stop sharing, right?
And then you can go to the PPT.
This here. So it's somewhat different than so that we are working on, right? So let's go to desktop. I think we had saved that on the desktop. So it's so where did it
Is it the
go?
one on the bottom? You can minimize this one.
Okay. This here.
Yeah.
Yeah, these are the ones. Yeah, these are the ones. So you want to show these slides, right?
We can close the other PPT just over.
So which is
The left one.
left one here. Close. Okay. Okay. Still close. But anyway, this is the one, right?
Probably just save as and just save it with some other name.
Yeah.
Just so that it goes away.
Oh, yeah. Very good. Very good.
Now close it. Actually, we renamed this one. We renamed this one.
Mm-hmm. Mm-hmm. Yeah, we can change it there, right?
But this is the one you have to
Yeah. Yeah. Okay. Very good. Okay, so to go to the slides, I go to share here, right? And then share this one here. And go to the slide mode. Okay. All right. So here we are. So this is the course that we are going to be talking about for the next 3 days: electric control and electric drives, analysis, simulation, and practical implementation for electric vehicles, wind turbines, and robotics. And uh, myself and Siddharth Raju, we are the two presenters of this course, and we are both with the Department of Electrical and Computer Engineering at University of Minnesota. So one of the big applications, emerging applications of electric drives is in wind turbines. And if you look on wind turbines, we are focusing on because the climate change is a big issue. And as you can see from this slide, wind is 100 times cleaner than coal. So that's the direction we should go to. And if you look at the structure of a wind turbine, what you see here is that in the nacelle, you have a gearbox, could be direct driven, and therefore no gearbox. But usually there is a gearbox in on land wind turbines, and there is a generator, and then power comes down to a 100 meters or 3 feet long cable, and power electronics converter at the bottom and the transformer. So it's somewhat of a common structure. And but the point that we are trying to make here is that there is a generator in the nacelle. Okay, and so other applications, emerging applications, is in electric vehicles, a little bit futuristic here. It's not on. It's not okay.
Right.
Okay, so, but you have to go and see if it's proper, you know. So one of the emerging applications is in electric vehicles, and this is maybe perhaps a little too optimistic that we have a autonomous vehicle and which could be driven, which may be an electric vehicle. So that will kind of revolutionize transportation. And as you can see from this graph, the carbon footprint of transportation sector today is greater than electric power sector. So each one of them in the United States, this is in the United States, each one of them is responsible for about 1/3 of carbon emission. So electrifying transportation is a big motivation, and it uses electric vehicles. One of the examples is in the planes. Again, you have electric drives to control various surfaces, and then NASA is working on some new designs for all electric planes, and electric rails could be another big applications of electric drives, and people are looking at these high-speed rail corridors in the United States. Not much has happened, but hopefully it happens. And also, for defense, anything that moves that requires electric vehicles, and in factory automation, that's another big area where you need to precisely control speed and position. So that's what this course is all about. Okay, and so if you look at also, not to forget that conservation, of course, but energy efficiency improvement is very important as well. So this slide shows that motors, 51% here, and also in heating, ventilating, and air conditioning. So if you combine HVAC and motors explicitly here, you see that together they correspond to roughly 2/3 of all the energy that we consume. And one way we can increase the efficiency of the system is shown by these two diagrams on the right. If you have a pump-driven system, where you have a motor that is running essentially at constant speed, this pump, then to control the flow rate, you need a throttling valve to reduce the flow rate, for example. You close down on throttling valve, but if you have an adjustable speed drive, you can control the speed of this pump and hence control the flow rate without wasting energy across the throttling valve. So in pump-driven systems, having power electronics and electric drives can be a big source of energy saving. And then, this is a slide I got from my former PhD student, who is now professor at University of Wisconsin-Madison, Eric Severson. So electric drives may also be used for energy storage in the form of flywheels. So these are some of the applications. So what is an electric drive that we are talking about in this course? Well, it's really shown in this block diagram here, where the electric input is usually from the utility, and the load may be whatever it is. But electric drive that we can think of consists of power electronics here, power processing unit, and the motor that is driving, and then sensors and controller is shown here. And the objective here is to very precisely control position and speed depending upon the application, of course. So a good example would be that, let's say that the load torque at some time, 0 in this case, as shown, takes a step jump, okay? And the objective may be to keep the speed constant, just as an example. So how can we keep the speed constant if the load torque has jumped as a step? Well, we can only do that if you also make the electromagnetic torque that the motor produces also, if that takes a jump, okay? So to make that happen is where vector control comes in, and we'll discuss that in great detail in this course here. So there are two underlying books. One is for basic electric drives, and the other one is for advanced electric drives. To follow this course, to use the material in this course, there is no need to get these books, but only if you wish to use them in your course. And then we also have a lab which goes with it. And so this is a very unique sort of arrangement here, where you can simulate your system, your controller for vector control with this drag and drop arrangement. The software is totally free to download, and with a single click, you can then, whatever you have simulated, you can go to real time by means of the controller. And this is a 3-inverter board which can control 3 motors essentially, and the motor sets are shown over here. And these can all be obtained from this source at this website here, cyamble.com. And so just as a disclaimer, I don't have any financial interest in it, but this is a startup which has in which our university has an equity stake, and so it's a very low-cost setup. So with this, I think we'll go to the video, and to do that, I think, Siddharth, what do I have to do here? Stop share, right? Okay.
And then you go to Chrome.
Then do here.
Yeah. You can start share, but switch over to Chrome.
Okay. So
the last one.
Okay, here.
Yeah. You go to share.
Share. Okay.
And then you can
go to Chrome, which is this here. Okay. So here we start with what's the module number we said? This one here. Introduction to AC Drive. So the idea is that we will look at these recorded videos, and if you have any questions after each video is done, we can chat about it. You can send your questions through the chat box, and we then go to the next video. So that's the plan. So let me double click on this, and it shows up here. And And if I maximize this, and so and click on this here, right? Sure.
They're not hearing.
This module introduces AC machines. And so here we will see sinusoidally distributed windings. I'm sorry. Let me just change this here to a pen here. We'll look at, ideally we should have a sinusoidally distributed winding. Air gap field distribution due to such windings. And usually we have three phases. So what happens when we have three phases excited simultaneously, and how we can use space vectors to represent sinusoidal distribution. So that's the topic of, or topics of this module. So we have primarily two types of machines. One is induction machine, and another one is permanent magnet AC machine. So we'll look at both, but they have different rotor construction. But on the stator, you may say that they both have three-phase sinusoidally distributed windings as shown here, phases A, B, and C. And so they are represented by these three windings over here, and their magnetic axis is also shown as A, B, and C over here. And we'll assume the rotation to be counterclockwise here. So let's just look at one of the three phases, phase A, for example, as shown over here. And ideally, so this is ideally speaking, we would like a sinusoidally distributed winding for phase A. So you can see that the current is going into one conductor, 1, and is coming out of 1 prime, is going into 2, and then it comes back and comes out of 2 prime, and so on. But as shown here, the conductor density distribution is sinusoidal in the sense that there are very few conductors along theta equal to 0, which is the magnetic axis, and maximum number of conductors 90 degrees from this magnetic axis here. So this conductor density distribution can be represented between 0 and pi in this range over here by this expression here, some peak value times sine theta. So you can see when theta equals 0, you have very few or 0 conductors, and similarly at pi, but at 90 degrees we have the maximum. So if we integrate this from 0 to pi, we can see that we have total of n sub s number of conductors on each half here, and this is equal to 2 times the peak conductor density here, n sub s prime. Okay, so that's how these conductors are sinusoidally distributed within this winding over here. So given this, we can find what the, let's say we produce or send a current IA, what would be the field density distribution, or magnetic field intensity distribution here. So we can take a path here at some angle theta here. Let's say you have H A sub A crossing this along this air gap here, and minus H sub A over here, but in magnitude they are the same. And so using Ampere's law and going through these equations, we can see that at any angle theta, the field intensity can be expressed by this expression here. So it depends upon the angle theta, and of course it depends upon the current at that instant. That is, so this is at any instant of time, let's say t1 over here. Okay. So given this here, field intensity, we can find the flux density and we can find the MMF distribution as a function of theta. So all these quantities have the same distribution, but they have different magnitudes and units, but the same shape. So what we are showing here is that at T1 and T2, let's say we have some positive value of I sub A, and the field distributions are shown here, whereas at T3 and T4, we may have negative current, and the field distributions are shown accordingly. But the point to note here is that the field distribution, whether it's flux density or whatever, is maximum along this magnetic axis here of this phase A. Similarly, it will be maximum along the magnetic axis of phase B and phase C here. So, that is what's shown here, that for three different values of currents flowing in these three windings, of course, all these three have to add up to 0. And so each one in the air gap is producing this flux density distribution, and the resultant of these three can be obtained point by point by adding them up at each value of theta, and that is given by this here. So this is pretty tedious stuff. You have to add point by point, but why not use vectors? So that's what we'll do. We'll use space vectors to represent sinusoidal distribution. So at any time t, whatever that time is, and whatever current we have in any given winding, that particular winding is producing a field distribution which is sinusoidally distributed. And you can see that if the current is in phase A is positive, the field distribution would be peaking along phase A magnetic axis. So we can represent that by a space vector. So a space vector has the orientation where the field distribution is peaking, and it has the amplitude based on how much is the peak of that field distribution. So here is an example where you have certain value of IA, which is positive, certain value of IB, which is negative, and certain value of IC, which is negative, but with the sum of all these three currents is equal to 0. And because of this IA, we have the MMF space vector for phase A in this direction. Because of B, which is negative, instead of being along the B axis, it's opposite to B axis over here. Similarly for C, since the current is negative, it's over here. And so to find the resultant MMF distribution, rather than adding point by point, we can add these three space vectors vectorially as shown here, FA, FB, and FC over here. And so the resultant space vector is F sub S over here. So that very easily gives us the orientation where the resultant flux density distribution is peaking, and it also tells us how much that is. So mathematically, that is what's shown over here. So here is an example where IA is 10 amperes, IB is minus 10, and IC is 0. Some very simple example over here, and we are asked to find the resultant flux, MMF space vector here. So it's very straightforward. We plug in for IA here, IB for here, and IC is 0, and we find this, and that is what's shown over here. So we will take it from here and see how we can use it. So here is the summary of this module. It shows that we have, ideally in an AC machine, sinusoidally distributed winding for each phase, but that's not usually what we have, but we try to approximate that, and we can discuss that more. Then because of these sinusoidally distributed windings, we have air gap field distribution, which is sinusoidal, and in most AC machines we have 3 phases which are simultaneously excited, so we can make use of space vectors to represent these sinusoidal distributions. This module introduces AC machines. And so here we will see sinusoidally distributed windings. I'm sorry. Let me just change this here to a pen here. We'll look at, ideally we should have a sinusoidally distributed winding.
Serious drawback of Zoom that people can unmute themselves.
Yeah.
Huh?
No, we can.
Start? I mean,
So, yeah, there is no
how far were there? So it was done?
Yeah, that was done. So
Okay.
we restarted it.
Okay. So
Now
we
we
should go
are-
to the next one,
Yeah.
right? So I should unmute here. No.
You can mute yourself.
But I could say that, okay, so now we'll go to the next video. And to go there, Jaram, I
Yeah.
share and then
Yeah.
go here. Okay,
Yeah. It's okay.
here.
So which module are we talking about?
Now I think we should go to that website to see those modules. This is electric drives, basic course. I'll know if you go to the Drupal site, cusp site.
Oh.
We don't, yeah. Okay, so here, what we just saw was
Module 16 purpose.
16.
Yep.
Okay.
We just got done with 15. So
15. Yeah, 16 here. Okay. So this one here. Okay. Mm-hmm.
So in this module, we'll look at how we can represent voltages and currents in machines in terms of space vectors. And these space vectors are very compact notations, and moreover, they give us a very good physical interpretation as to how these machines operate in the first place, and later on, how we can control these machines using this space vector analysis. So let's start with this current space vector in the stator winding. And here, we have 3 individual windings with currents IA, IB, and IC. But we can create this stator current space vector represented with this arrow on the top here at any given instant of time by taking instantaneous phase currents and multiplying them with their axis orientations, like 0 degrees, 120, and 240, and then summing them up. So we get a combined current space vector, as you can see here, which has an amplitude in this complex expression, an amplitude, and a phase angle over here. And similarly, we can do for phase voltages. So it's very useful to at least get the physical interpretation of the current space vector. So to do that, we will multiply this current space vector definition we had in the previous slide with the number of turns which in each phase, that n sub s, by 2. So doing that gives us the MMF, as you can see from this first equation, the MMF associated with each of the phase windings, MMF that is impressed on each of the air gaps, and then when we sum them up, that gives us the combined stator MMF, as you can see here, F sub s. And so what we see that the stator current space vector is represented is related to the MMF space vector by this number of turns over 2 factor. And so similarly, the amplitude of the stator current space vector is related to the amplitude of the MMF space vector, and similarly, the angle at which this current space vector lies at any instant of time is the same as at which this MMF space vector would lie. So, what we are saying basically that these two are collinear, and of course, the flux density space vector is related to the stator current space vector over here. So the bottom line is that the magnetic field that is produced in the air gap is a combined effect of these 3 currents in phases A, B, and C, but equivalently speaking, we can say that we have a hypothetical winding, as shown on this figure on the right. And this hypothetical winding has sinusoidally distributed turns, n sub s, number of turns, and it has a current that is flowing, which has a value of is hat over here. So each turn has this current is hat, but the number of turns are sinusoidally distributed. And the MMF produced by such a hypothetical winding with this orientation that we see is the same as the currents produced by IA, IB, and IC flowing individually in these 3 phase windings. So this is very helpful in describing in calculating the torque expression, as we'll see. And here is, if just to show that BS and IS are collinear at any angle, and similarly here, BS and IS would be along this axis over here, right here. So, we saw that we could go from phase currents to the stator current space vector, but how about the other way around? Well, it is certainly we can do that if somebody gives us a current space vector. We can find what the individual currents are associated with these 3 windings, and this is made possible because we have a constraint here that the sum of these 3 currents by Kirchhoff's current law, IA plus IB plus IC is equal to 0. So making use of that, we can mathematically, graphically, as shown in this slide, we can find, given a current space vector, stator current space vector, we can find what the components IA, IB, and IC would be. So what happens under balanced sinusoidal steady-state excitation? So let's say we have this 3-phase winding in the machine, and right now we're just considering let's say, the magnetizing currents. The rotor is open circuit, electrically open circuited, and we have these 3 currents, IMA, IMB, and IMC, and they are sinusoidal. And arbitrarily, let's say that the time origin, t equal to 0, is at an instant where the current in phase A is peaking, and its amplitude is Im hat here. So the question is, what happens to the stator current space vector defined in terms of these three phase currents. What we'll see that if we substitute for the stator current space vector these phase current components into it, we'll find that this stator current space vector has a constant amplitude, which is this here, and it rotates at a speed which we'll call synchronous speed, omega. And this omega is 2 pi times the frequency of these phase currents that we are applying here. So that's what this diagram in the middle, of course, is showing that these three currents are sinusoidal, and they are 120 degrees apart, and they have equal amplitude. And what we see on the right side of this diagram is that the stator current space vector is rotating at a synchronous speed, omega, which is 2 pi times the frequency. And so at time 0, it's along the phase A axis, because we chose the time origin to be at an instant where the current in phase A axis is peaking, but it is continuously rotating at a synchronous speed. So at, let's say, at 120 degrees, which is 2 pi over 3 radians later, it is the stator current space vector is peaking along phase B axis, because at that instant of time, the current in phase B is at its positive maximum. So we can see that mathematically over here, and the bottom line is that we have a rotating MMF distribution in the air gap, and this flux density distribution is also rotating, and the amplitude of this distribution, distributions, is constant under sinusoidal steady state conditions, balance conditions, and it is rotating at a synchronous speed omega. Now, we should be able to make a relationship between, under this balanced sinusoidal steady state excitation, between space vectors and phasors. So let's do that. And so again, defining the time origin to be when the current in phase A peaks. And let's say we are looking at some instant of time. Well, here, we could look at some instant of time where current has some other value, not the maximum value. So I sub A in time domain, as you can see, is given by this expression, where time could be anything. So in this case, what we have done is, in fact, at omega t equal to alpha is when the current is peaking. So the time origin is not chosen to be when the current in phase A is maximum. If I said that earlier, I was incorrect. It's somewhere other. But at omega t equal to alpha, as you can see from this diagram, the current in phase A peaks. So given this time domain expression for current I sub A, we can write a phasor expression, which will be, if using the peak value of this current as the amplitude of this phasor, Im hat, and the orientation would be minus alpha for the phasor representation, which is shown in the phasor diagram on the right-hand side. So what happens to the space vector? Well, we know that the space vector is, for one thing, it has a constant amplitude, but it peaks along, it will be along phase A axis when the current in phase A is at its maximum. That means having chosen the time origin as we did in this diagram, it will peak, or it'll be along the phase A axis alpha degrees later. So at time t equal to 0, this steric current space vector is alpha degrees behind. And that is what is shown in this diagram. And mathematically, we can see that the amplitude of the steric current space vector is 3.5, no, not 3.5, 1.5 times, the 3/2 times the amplitude of each of the phase currents here. So that's the relationship between the amplitudes of the phase quantity and the combined space vector quantity. And the other thing we notice is that the orientation of the phase, the phasor associated with phase A is the same as the orientation of the space vector combining all three phases. So that is shown in this diagram here. So this orientation here is the same as this orientation over here. Okay. Now, we can also get at the voltages induced in the stator winding, knowing that we have these three currents flowing in these three phases. In this case, rotor is open, so it's only the magnetizing currents. So, we can take the time origin anywhere, but let's say that it's at an instant when the phase voltage in phase A peaks. So if that's the case, this EMA would be at its, it will be horizontal, and under this condition, these three windings appear just purely as inductances. If you ignore the resistance of these windings, so you can see that we can, first of all, in this diagram in the middle here, we can represent all three voltage phasors for phases A, B, and C, and similarly the currents associated with them are 90 degrees behind, and again for all three phases. But taking this, we can go to the next step where we say that first of all, the equivalent circuit for this phasor diagram is shown over here, but we can also express these phase quantities by means of space vectors. And certainly at time t equal to 0, where the voltage in phase A is peaking, therefore the combined EMF space vector would be along the phase A axis as shown in this diagram here. And similarly, the current space vector would be 90 degrees behind, and it will be with the same orientation as the phase current A over here, as we had seen in earlier slide. And we know that if L sub m is the magnetizing inductance, then the voltage induced in phase A is related to the derivative of current in phase A by this L sub m. So we can write such equations for all three phases, where if you just strictly talk about a two-pole machine, this can be generalized for p-pole machines, of course. The magnetizing inductance can be calculated to be this expression, not that we need to necessarily calculate that for our purposes, but it is helpful to see the relationship between this magnetizing inductance and the number of turns, the length of the machine, the rotor, the air gap length, and all those things here. But given this magnetizing inductance, we can calculate the relationship or express the relationship between the induced voltage because we have these currents into these windings, and so this voltage induced related to the rate of change of the current in that phase. And so here this magnetizing inductance L sub m includes the the mutual effect. So mutual inductance from coupling from phases B and C are included in phase A, and similarly in other cases. And we can also see from this space vector diagram is that the voltage space vector is leading the current space vector, as shown in this equation, by 90 degrees, and the relationship is given by omega L sub m, which will be a direct result of converting equations like this into a space vector equation shown over here. So it's a very compact notation, and we'll see how it could be extremely useful having this phasor representation for understanding these machines, calculating the torque expressions, and so on. So here is a simple example where we have 3 applied voltages, and again, rotor of the machine is electrically open circuited, and there's no permanent magnets or anything like that on the rotor. So it's basically an inductance for all practical purposes, ignoring the resistances of stereo windings. And we can calculate, given these phase voltages, what the voltage space vector will be. And then, using the expression in the previous slide, we can easily calculate what the stereo current space vector will be. And we can also individually calculate what the phase currents will be at any instant of time. And we can also calculate what the flux density space vector will be in this machine. So this brings us to the end of this module, where we have looked at the use of space vectors to describe voltages and currents, and we have given a physical interpretation of the current space vector and how we can calculate the components given a current space vectors in terms of individual phase currents. And we can also calculate what the induced EMF would be in these phase windings because of these currents. And then we saw the relationship between space vectors and phasors. And so it's a very useful way of looking at analyzing these machines, and then later on controlling them.
Next, I can come on here, right? Stop share. Okay. All right, everybody. So I don't see any questions here. Yeah. So we go on to the next one. And so Jairam, if you could help me to go there. So share, and then this, and then the module number after that.
So in this module, we'll look at how in this module, we will look at a very important class of machines called permanent magnet AC machines. And in the past, these machines were used at fairly, they were limited to a few kilowatt, let's say, in rating. But now they are being used in fairly large sizes, such as for wind generation up to 5 to 10 megawatt level. So, we certainly should know how these permanent magnet AC machines operate, and then later on how to control them. So we will begin with a simple description of what they look like, how they operate, and how the torque is produced in these machines. And also we will look at, in a very simple way, how we can supply the currents into these machines to control them. So let's look at the block diagram here. They are always, most of the time anyway, operate in a closed loop fashion here, as shown by this block diagram, where we have power coming from the utility, and then we have this power processing unit made up of power electronics that, under the direction of this controller, is supplying these currents into this sinusoidal PMAC motor that we will see in a minute. and driving this load, but we also need to sense the position of this rotor, as we'll see the need for that. And that sensed position at any instant of time goes into the controller in order for the power processing unit to determine what currents ought to be supplied. So let's look at the structure of this type of machines. On the stator, we have a sinusoidally distributed three-phase windings, as we have seen in previous modules in a general AC machine. But on the rotor, we have permanent magnets. So here they are represented as north and south poles, just a two-pole machine, but it could be any number of pole pairs. But it sort of makes it simpler just to talk about just a single pole pair as shown here, and how these north and south pole are, these magnets are attached to this rotor are not described except to show that we have a north pole on one side and the south pole on the other side. And we will measure the rotor position, theta sub m, as shown here, with respect to phase A axis. So as the rotor rotates, this theta sub m would change. And so these magnets are also arranged such that they produce a sinusoidal flux density distribution in their gap. So we can represent that flux density distribution by a space vector, B sub r, as shown over here, the space vector. And of course, its amplitude remain constant, but its orientation, this theta sub m, would change as this rotor rotates. So the next thing is how do we get some torque out of this generator or this machine, whether in a motoring mode or in a generating mode. So what we see here is that first of all, the flux density distribution produced by the permanent magnets in the rotor is represented by this equation here, and on this diagram by this space vector over here. So what we really would like to do, and we'll show that in this slide as well as in the next, that in order to get the maximum torque per ampere, we should place the stator current space vector 90 degrees ahead of the rotor flux density space vector 90 degrees ahead in the direction of rotation. So this is being described in the motoring mode. So if you want to make this into a motor, we would like the stator current space vector to be placed 90 degrees ahead of B sub r space vector in the direction of rotation. So in this case, it's in the counterclockwise direction, like this here. So by placing this stator current space vector 90 degrees ahead, as we saw early on in a previous module, that there's a physical interpretation associated with this stator current space vector. That is, it is representing a hypothetical winding which has an orientation such that its MMF is along the stator current space vector, and it is sinusoidally distributed as shown in this diagram over here. So if I sub s is over here, then this hypothetical winding has the magnetic axis along the same axis as I sub s, and it has this current IS hat flowing through each of the conductors, and you can see that the maximum conductor density then is where the flux density distribution is maximum. That is where the stator, the rotor flux density space vector is oriented. So the maximum current density, conductor density, I should not current density, but the maximum conductor density of the stator is at the same location where the maximum flux density is produced by the rotor. And this we can prove would result in maximum torque per amp. So first of all, we could have taken any general orientation of I sub s, but we can just physically see that if it was not in the orientation as we saw earlier, some conductors would be producing a torque in the opposite direction and compared to the others, and that will not be the optimum condition. So 90 degrees is the optimum condition, and we can calculate the torque that will be produced, although we may not be using it, but it's helpful to know. And that we could do by, first of all, to make our life easier, say that this B sub r space vector is horizontally located like this. In that case, I sub space vector is over here, and we can see this hypothetical winding orientation, and we can take some angle zeta, and in this differential angle d zeta here, we have this many differential number of conductors. The current is Is hat. The length of this this machine, let's say, is L. So that's the conductor length. And the flux density at zeta, in terms of its maximum Br hat, is this here. So using this fundamental principle that the force produced is BLI, we can calculate the torque, or differential torque, in this differential number of turns by multiplying this force by the radius r over here of the machine. And then to find the total torque, we integrate from zeta of minus 90 degrees to plus 90 degrees. And just by symmetry, we just need to do that and multiply by this factor of 2, and we get this expression over here. So what we see here is that this torque that we have is proportional to this Is hat, the maximum value of the stator current space vector, and it's related to the machine quantities, which are not going to change. The number of turns, the radius, the length, the peak of the magnetic, the flux density that is produced by the magnets. So what you see here in brackets, that's really a constant K sub t, which we'll call a torque constant, and its value is over here. And the electromagnetic torque produced is equal to this torque constant times Is hat here. So just like in DC machines, permanent magnet DC machines, we can control the torque by controlling the armature current. Similarly, in these machines, so-called brushless DC machines, because there are no brushes, we can control the torque by controlling Is hat. So that's why this name brushless DC. So that's the similarity that is shown in this slide, where we have in a DC machine magnets on the stator, and on the rotor we have an armature winding, and which produces this armature flux phi sub a, which is at 90 degrees to the stator flux, which is stationary because the magnets are stationary, and we get the torque controlled by the armature current here. Whereas in this brushless DC machine or PMAC machine, we see that we have magnets on the rotor, and this rotor is rotating. Therefore, this B sub r that we get is rotating but intentionally we put the stereo current space vector always 90 degrees ahead of the flux density space vector BR in the direction of rotation if you want to make this into a motor, and it will be 90 degrees behind if this were to be a generator. And you can see that there's a great deal of similarity here. The only thing is that we need to make sure that we have appropriate currents in phases A, B, and C to put the stereo current space vector 90 degrees ahead of B sub r space vector here. So we know this electromechanical equation here that the acceleration is dependent upon the difference between the electromagnetic torque that is generated and the opposing load torque, and divided by the equivalent inertia of the system, assuming damping to be negligible here. So that's the acceleration, and which is d omega dt, and therefore we can calculate what omega would be, this initial speed plus the acceleration over time. And similarly, knowing the speed and knowing the initial position, we can calculate what the position of the system would be at any instant of time t, which is the initial position plus the integration of the speed over time. So if we wish to exert or derive certain amount of torque, then we need to know the motor torque constant kT, and also we need to supply appropriate currents in these three phases at any instant of time, such that this IS vector is 90 degrees ahead of the B sub r vector, and it has the right amplitude. So to find the amplitude, knowing the desired torque that we need to produce, and knowing this motor torque constant, which may be in the motor data sheet, we can calculate what the amplitude of this stereo current space vector would be. And knowing the position of the rotor that we have to sense, and knowing that the stereo current space vector should be 90 degrees ahead, we know what the orientation of this current space vector would be. So knowing these two quantities over here, we can at any instant of time calculate what this stereo current space vector is. And as we saw in the earlier module, since these three currents add up to 0 due to Kirchhoff's current law, we can individually calculate what these three phase currents ought to be supplied to this PMAC machine. So this is sort of illustrated by means of a simple example where K sub t is given as 0.5 Newton meters per amp. And in this case, we need to produce a holding torque. That means it's given that we need to hold the rotor for whatever reason at 45 degrees with respect to phase A axis. So given that, we can calculate what the currents in phases A, B, and C need to be. And they turn out to be as shown in this example of these values over here. And these are DC currents. So it's a PMAC machine, but so you can also see the power of space vectors, that they work with DC quantities, because the sinusoidal distribution is coming from the fact that these windings are sinusoidally distributed. So in each of these three windings, the current that are being supplied are DC, because we want to hold the rotor at a constant angle of 45 degrees. It's not moving, right? So the currents are also, current also should not be changing with time, so they are DC. But we are able to apply this space vector concept very nicely here. So that shows the power of space vectors. So here it brings us to the summary of this module, which shows that we can that we have looked at a very important class of machines, PMAC machines, and how they operate, how we can calculate a torque in them, how they are similar to brush type DC machines, and we can also calculate what the currents have to be and where they have to, and well, let's just put it, what these currents have to be in each of the 3 phases to supply the torque in a way that torque per amp is maximum.
Okay, so uh, this comes to the end of our this present video, and let's take about a 15-minute break, and let's come back at 9:45, and then we start with the next one. Thank you.
So welcome back, everybody. Before we proceed, I would like to answer the question that was posed to everyone. So basically, why does the winding have to be sinusoidally distributed? So it is necessary if you want to reduce the harmonics in your torque. So when we later derive the torque equation, you would see that only if the windings are sinusoidally distributed, as well as the voltages that you apply are sinusoidal, you would have a torque component which ends up being a constant. If there are, if the winding is not sinusoidally distributed, if it is having a constant magnitude, then your torque component is going to have additional harmonic content in it, which is going to cause oscillation and losses. So that's the reason why we do sinusoidal distribution. Um, in practice, it's not always ideal to maintain a sinusoidal distribution, though. So if you see an induction motor, one of the problems is a phenomenon called crawling, because even though we want sinusoidal distribution, due to a discrete number of slots available, the distribution is not going to be, it's going to be a step sinusoid. So what this is going to cause is higher order harmonics are going to come into the picture. And what will usually happen is when a induction motor is starting, when you, especially when you're controlling with a drive, and if you apply a very high frequency component, like seventh order harmonic, it usually gets stuck in those value, and the torque curve characteristic does not reach all the way to full load condition. So this is a very common phenomenon that happens in all practical motors, and there are multiple ways to avoid it. And one of the ways to make sure that your winding is sinusoidally distributed. And hopefully that answers your question. And if not, please send in message again, and I'll try to answer it better. So let's proceed with the next video. This is on the continuation of PMAC. We'll go over the equivalent circuit and control of PMAC speed control.
In this module, we will see how voltages are induced in PMAC machines and what the per phase equivalent circuit looks like, and how we can control these machines. So in the earlier module, we saw that these machines are controlled by injecting currents into them, but as a consequence of injecting these currents, voltages are induced. One is that we have a permanent magnet on the rotor under balanced sinusoidal steady state condition are caused by two reasons. One is that we have a permanent magnet on the rotor producing this B sub r space vector, and this is rotating past the stationary phase windings at a speed omega sub m. So certainly there'll be induced back EMF induced in each of these windings. And similarly, we have this current space vector I sub s, which is producing its own flux density distribution, and that distribution is rotating past the stationary phase winding. So we again would have induced EMF in these phase windings, and the total induced EMF is really the sum of these two. So let's look at first the induced EMF due to the permanent magnets on the rotor, which are rotating at speed omega m. And this first equation is just to remind us what we have seen in previous modules. But in this case, we have a flux density distribution produced by the magnets on the rotor and given by the space vector Br. And therefore, the space vector representing the induced voltages in the stator due to this would be given by this space vector over here, where B sub r is over here.
and the relationship is expressed by this equation over here. And we can see here that what we have is this induced EMF, which is proportional to the proportional to BR, and is related by this two factors. One is the speed omega sub m, and the other one is what we'll call in the quantities within this bracket as voltage constant Ke in volts per radians per second. And actually, it's more than this voltage it's more than this voltage constant Ke. But let's define this voltage constant Ke in volts per radians per second to be the same as this torque constant Kt, which we have seen in the earlier module, which was Newton meters per amp, and which had this expression over here. So if you make Ke and Kt the same, then this quantity within the brackets over here is 3/2 times Ke over here. So we get this expression here, which shows that this induced voltage space vector is given by this, and if you recognize J as being 90 degrees, we can take this J and instead of having just theta sub m here, we can make it theta sub m plus 90 degrees over here. So bottom line is that this induced EMF in the stator windings due to the permanent magnets on the rotor are related by the voltage constant and the speed of rotation here. Okay. Then the next thing we have to look at is the induced EMF in the rotor windings due to the fact that the current space vector is also rotating at speed omega sub m in steady state. And we have seen this equation before, where the induced EMF is 90 degrees ahead of I sub s over here. And so we can, again, making use of the magnetizing inductance, we can come up with this expression of the induced EMF due to the stator current in terms of the stator current amplitude over here. Now the net induced EMF is the sum of the two, and we are showing this under this optimum operating conditions where the current space vector is 90 degrees ahead of B sub r space vector as shown over here. All right. So we can see that in this case, due to BR space vector rotating at speed omega sub m, we have this induced EMF in the stator phase windings represented by the space vector. And then due to this current IS, we have induced EMF, which is also 90 degrees ahead of IS, given by this space vector over here. So the net induced EMF is the vector sum of these two, and that's this over here. So having seen, and this is mathematically expressed by means of these three equations over here, and having seen early on the relationship between space vectors and phasors, this is at space vector at time t equal to 0, let's say, and what various phasors would look like. In phase A, the current phasor, the induced EMF due to the permanent magnets on the rotor, induced EMF due to this stator current space vector rotating, and the net induced EMF as a phasor in phase A. That can be represented by this diagram over here. So in this diagram, we add the leakage inductances which were ignored. So in a phase, we not only have the magnetizing inductance, but also the leakage inductance. So we can take that effect into account. And also we may have some resistance, R sub s. So this is in a phasor diagram, this is the induced EMF that we saw in the slide before, but to that we can add the drop due to the stereo resistance and the leakage inductance over here, and come up with this applied voltage V sub A phasor. So knowing this from this phasor diagram, we can, from these phasors, we can come up with this per phase equivalent circuit as this is the voltage that has to be applied to supply this current over here. And then we have this back EMF due to the permanent magnets on the rotor. Then if you include the magnetizing inductance, which represents the effect of the fact that we have a rotating current space vector, which is inducing EMF in the stereo phase windings. We have this phasor, and to that we add the drop across the leakage inductance and the resistance in order to come up with the phase voltage that needs to be applied to get this current IA over here. So once again, we have, in order to see how what we need to do, let's look at this block diagram here, which shows that basically we are injecting currents IA, IB, and IC as a function of time, knowing the rotor position. And of course, these currents IA, IB, and IC have to be supplied in opposition to induced back EMF and these are supplied by this power processing unit, where the power is coming from, in most cases, the utility, but need not be maybe through batteries over here. So in a very simplistic manner, we can show what is going on. Just let's take the case of phase A. This controller is telling us this is the reference current that needs to flow in phase A, and we can actually measure this current, and the difference of these two goes into this hysteresis block over here in this comparator to tell us what the switch position should be, and that is represented by these waveforms here. Let's say you want reference current, which is in the middle of these two dotted bands that we see, and we can force this actual current in phase A to be within this band by controlling the position of the switch in this power processing unit. If the current goes above the top band, we change the position of the switch to be in the downward position, and vice versa. So by this hysteresis current control, we can get the desired currents to flow in this machine. But of course, there are much more, there are better ways to achieve this, but without, and through power electronics, but without going into the details of that, for our purposes, it should suffice here. So here we have a very brief summary of what we have seen in this module. First of all, that we have induced EMFs in the stereo windings, and we came up with the per phase equivalent circuit, and then we saw how we can supply, at least in a very simple manner, perhaps simplistic manner, currents into these three phases of this machine.
So we have a little bit of extra time in our hand. So before we proceed with the next video session, which will be on induction motor, I would like to show you a little bit of simulation of permanent magnet motor hysteretic control that was just discussed by Professor Mohan in the previous video. So let me go ahead and share a simulation that was already built. Hope you all can see this. And so what we have in this model is basically a permanent magnet motor on the top here, and it's modeled using BQ. So that's what we are going to be learning later in the day tomorrow, modeling of a permanent magnet motor. For now, let it be a black box. You've given 3 input variables: the voltage and the speed, and the output. The motor model will determine what the current an actual motor would consume if you apply these voltages at that particular speed, and what torque could be produced. As Professor mentioned, hysteretic control is really easy to implement, but it has a major shortcoming that the switching frequency is not constant. So design of filter, this causes a lot of EMI issues specifically, which cannot be abated in any good manner because the frequency is all over the place. So in this model, we'll just take a brief look at how the currents look and the speed looks when we do hysteretic control. And again, this was just for learning purposes, and it's not usually used in any industry, this kind of control. So here we have the permanent magnet motor model, and on the left we have the hysteretic control. So the control, as mentioned, is really simple. You have the reference currents, 3 sinusoidal current, and then you compare it to the feedback. And if your reference current is greater than your feedback current, then you just turn the switch off so that the current dies down. You turn the switch on so that the current builds up to the reference. And if your reference is lesser than your feedback, you turn the switch on so that you turn the switch off so that your feedback dies down and matches with your reference. So that's all it is, basically turn on and turn off. And you give like a small amount of delay before you do that, hysteretic band, basically, not a delay. And so what we are doing in this simulation is we are giving a step speed reference. We are stepping the speed from initial of 0 radians per second to 150 radians per second, and we'll observe the speed matches our requirement. And what we are additionally doing as well is we are emulating a load. So in an industrial setting, you would have a permanent magnet motor, which is, say, in a robotic arm, which would be carrying a load from ground and moving it to another place. So that can usually be modeled as a step load or a ramp load, or depending on whatever the condition is. So in this case, we are trying to emulate a step load. So we have a DC motor which basically behaves as if it's an actual load. And we do this in the lab, which we will see later in the day today. But for now, we have just modeled the DC motor in the simulation, and we emulate a step load using that. So let me go ahead and run the simulation. And again, how to build this model and everything we will be dealing later today. I just wanted to give you like a brief glimpse of it before we go with the next video, since we have a little bit of time in our hand. So first, let's take a look at the speed feedback. So as I mentioned, initially the speed is at 0, and we are stepping the speed to 100 radians per second. And you can see the speed ramps up and then settles down at 100. So this initial ramp is because if you look at in our PI controller, the integral has a saturation, and as well as the sum of the PI itself is saturated out at 5 ampere plus or minus, so that the motor current is not exceeded. And that's the reason why this kind of nonlinear ramp comes into the system. If that saturation is removed, it'll be like a perfect underdamped response that you see in all textbook. It just immediately shoots up a little bit, like around 20-30% for the given PI value, and then dies down and then settles much faster than this. So this slope is due to the saturation block that we have. And at about 3 seconds, we apply a load that is right here. So at 3 seconds, we apply a load using the DC motor, and we see that the speed kind of dips a little bit, but then the PI controller adjusts and brings it back to the desired speed again. How to design these controllers and stuff we will look at in a later video. For now, let's just assume that's the way it is. So the interesting thing is, even though the speed looks perfectly clean, because of the high amount of inertia present, if you look at the current, let me zoom in. So this is the current waveform. If you were to put a current probe on any industrial drive that you can buy off from Rockwell or Siemens, this wouldn't be the current. It'll be much smoother. Like this would be unacceptable because of this would cause an excessive amount of EMI interference, which could kind of disrupt all electronics in and around this drive. And as you can see, the switching frequency itself is not any particular value. It's all over the place because hysteretic control is not a switch, a constant frequency based control. So there was a problem that Professor was talking about, and another big issue that happens with hysteretic control is especially at really low currents, at low speeds, which would ideally lead to low current. You would see that the amount of harmonics as opposed to the fundamental component itself becomes really, really high. So this would cause a lot of torque oscillations in your motor. In this particular model had a lot of inertia on it. You don't particularly see any kind of oscillation on the speed. But this, if you put a scope to measure the torque, you would see a lot of oscillation on the torque, and this could damage or reduce the bearing life of the motor, in addition to all other sort of damage to the rotor shafts and stuff. So practically, this is not used for most scenarios, but it's just but it's much more easier to implement. And we will see how to get away from this kind of implementation later tomorrow when we go to vector control implementation. So with that, let me stop this, and we can continue on with the next video, which will be on induction motor, introduction to induction motor.
In this module, we will see a very important class of machines called induction machines. And they are used in very low power to extremely high power applications. And in very low power applications, of course, they are single phase. But in this module and in this textbook, we will basically concentrate on the three phase and single phase later on. So let's start, and we'll assume, of course, a balanced sinusoidal steady state operating condition, and this is in steady state. And first, of course, we'll begin by looking at the structure of these machines, and then we'll also look at part of the principle of operation. We'll go on for 2-3 more modules, but in this module, we will basically assume that the rotor is magnetically present, but somehow it's electrically open circuited. Okay, so let's begin. So just to talk about the applications, they are used in all kinds of general purpose applications where we need to drive something at we don't really care if the speed is exactly what it needs to be. So general purpose. Whereas there are some adjustable speed drives where we do care what the speed ought to be, and we need to vary that speed. So that, in general purpose, of course, it could be running at essentially constant speed, but in adjustable speed drives, we do want to control their speeds. And in servo drives, we may even want to control the position of the load through these induction machines, and certainly induction machines can be used. So wherever you see motors, think of them as machines, because we will look at them in both motoring as well as generating mode. Okay, so as far as the structure is concerned, just like in this previous PMAC machine that we discussed, these have a three-phase winding as shown here in a simple manner. Each of these phase windings is sinusoidally distributed, ideally speaking anyway, and has n sub s number of turns, and their magnetic axes are 120 degrees apart with respect to each other. Now, there are wound rotor machines, induction machines, but by and large, majority of them are squirrel cage. So that structure is shown here, where there are electrically conducting bars around the periphery of the rotor, and in some slots or something like that. And on the both sides of this rotor, these bars are electrically short-circuited by so-called end rings here. All right, so we will concentrate on squirrel cage induction machines. All right, so now the stator, first let's assume that the rotor is present but electrically it's open circuited somehow, as if those bars that you saw in the squirrel cage in the previous slide, they were somehow cut, so the current cannot flow. And let's make an assumption initially, and we will, include that later on. But let's assume that the stator resistance and the leakage inductance is 0. So it's kind of an idealizing assumption to a certain extent. And we are applying these 3 voltages across these 3 windings, balanced sinusoidal voltages. And these would result in magnetizing currents, as we saw earlier, in connection with our discussion earlier in earlier modules. Each of these voltages would result in a magnetizing current IMA, IMB, and IMC flowing. And under this assumption of 0 resistance, these currents would be 90 degrees lagging behind their respective phase voltages. So that's what is shown in this phasor diagram. And these currents would then cause a rotating MMF, rotating flux density distribution in the air gap. And this will rotate at a synchronous speed, omega sync, which depends upon the frequency at which these voltages and currents are applied, but also on the number of poles in this machine. So if it's only a 2-pole machine, then this expression applies. But if you have higher number of poles, p number of poles, let's say, then the synchronous speed is given by this here. So the synchronous speed is inversely proportional to the number of poles. But of course, it is proportional to the frequency of applied voltages and currents. All right. So, we saw this phasor diagram earlier, but we can also represent this in terms of space vectors. So these currents have phase currents have this amplitude for phase voltage having this amplitude here. L sum M is the magnetizing inductance. Then you can see that the current space vector we can generate from this phasor for I sub A. Phasor for I sub A is 90 degrees behind V sub A, which is shown horizontally here. So that's why the space vector has this minus 90 degree here, and the amplitude is larger than the phase amplitude by a factor of 3/2. Okay, so those things are included here, and you can also see that we can represent these phase voltages by a stator voltage space vector here, which again would have an amplitude 3.5 times larger than the amplitude of the phase voltage here. Here's the phasor diagram for phase A. Correspondingly, there's an equivalent circuit here, and this flux density distribution that is produced by all these 3 phases combined has a constant magnitude and rotates at the synchronous speed omega sync over here. So in this diagram at t equal to 0, if voltage in phase A is peaking, then V sub S space vector is along the horizontal line, and IMS is 90 degrees behind it. And similarly, this flux density space vector is collinear with the stator current space vector, and all these vectors are rotating in steady state at this speed omega sync. So we need to convince ourselves, and you can also see what the peak flux intensity is in the air gap, and similarly what the peak flux density of the distribution. This is the flux density space vector, and we can see that its amplitude, it's just mu naught times the field intensity, and so we can write this as flux density space vector as well. All right. So this brings us to the summary of this module. It's not much in it. That we first saw the application of these induction machines. from very mundane application to wind turbines, for example. A lot of wind turbines using induction machines as generators. We looked at their structure. They're at least in one form. We have a squirrel cage rotor, but certainly there are wound rotor induction machines as well. And then we looked at the principle of operation, where the rotor is electrically open. In this module, we will continue with the discussion of the operating principle of squirrel cage induction machines, and we'll see how voltages are induced in the rotor circuit, and thereby the currents flow and a torque is produced. So that's why these machines are called induction machines, because by induction, electromagnetic induction, voltages and currents are induced in the rotor circuit because there is no such winding there, just a squirrel cage, which is not really supplied by anything other than through this induction. All right, so to understand induction machines, I think this transformer analogy is extremely beneficial. So let's think of this transformer here with two windings, and I have purposely cut the core to sort of emphasize that in induction machines we have two air gaps. The flux path has to cross two air gaps. Okay, and initially, let's assume that the primary winding has no resistance and no leakage inductance. That is similar to assuming no resistance and no leakage inductance for the stator winding as we had done in the previous module here. So let's initially assume that load is not connected, and we apply a sinusoidal voltage to the primary, and as a consequence this magnetizing current would flow, and there'll be this flux phi sub m in the core. So now this in the absence of any resistance and leakage inductance, this flux phi sub m is completely dictated by the voltage being applied and the number of turns we have in the primary. And that's N1. Okay, that's Faraday's law. And there is nothing we can do to the secondary winding or on the secondary winding or in the secondary winding that will change this flux here. So if this flux, there's a time rate of change of flux, and that flux is linking with the secondary winding. So there's a voltage induced in the secondary winding, and if you connect a load across the secondary winding, there'll be current I2, and therefore there'll be an MMF produced by the secondary winding, which will try to influence or upset this flux phi sub m. But we agreed that it cannot change because it's totally dictated by applied voltage V1 and the number of turns, and the rate of change, the frequency at which the applied voltage is varying. So, this MMF that is produced by the secondary winding has to be canceled by additional current drawn by the primary from the input voltage here, I2 prime, such that flowing of I2 prime into the primary winding produces an MMF which completely nullifies the MMF produced by I2 flowing through the secondary winding here. And that's how the flux can get, flux remains unaffected by the load. And this is how the transformer primary knows that something has happened to the secondary winding, okay, because there is no electrical connection here as such, only a magnetic connection. And this is exactly what happens in an induction machine, as we'll see as we'll see later on. So let's look at how these voltages are induced in the rotor circuit. First, let's assume that the rotor winding is rotor bars are somehow open in the sense that there's no current flowing, just for the sake of discussion. And we are applying a certain voltages resulting in this stator voltage space vector, which is rotating at the synchronous speed, and it results in some magnetizing current which is drawn from the stator, and this flux density distribution is represented by the space vector, which is also rotating at the synchronous speed. But let's say that the rotor is rotating at a speed omega sub m, and this omega sub m is smaller than omega sync. It could also be greater, as we'll see for generator operation. But let's say that omega sub m is smaller, so the rotor is slipping. That's why it's called slip speed. With respect to the synchronous speed, the rotor is slipping at this speed omega slip, which is the difference of these two speeds. So as you can see that these rotor bars are cutting this flux density distribution. The other way to say is that this flux density distribution produced by the stator is rotating at a speed faster than the speed at which these rotor bars are rotating. So there's a cutting of flux, and therefore in each bar there's a voltage induced, and at any angle theta, for example, as shown here, this is the flux density, because flux density is maximum along this axis over here. So this is the flux density, and then so at a bar which is located at an angle theta, this will be the voltage induced over here, making use of that fundamental principle that induced voltages BLU. Okay, so you can see that in this picture, this bar over here under the maximum flux and this bar under the maximum flux, because the flux is like this, these two bars would have the maximum voltages induced, and the bars away from this axis here, away from them, they'll be cosinusoidally smaller, these induced voltages. All right. So now we saw that there are induced voltages in the rotor bars, and these rotor bars are, actually short-circuited at both ends. And by symmetry, you can see that these both bars are at the same potential, and therefore the induced voltages are dropped across the rotor impedance. But let's assume that the rotor leakage is negligible at this point. Later on, we will include it. It's very important for certain applications to include the effect of rotor leakage. But let's assume that the rotor leakage is negligible. So there's only the resistance of the rotor bars, and these bars are short-circuited at both ends. So you can see that the picture is somewhat like this, where the induced voltages in each bar is different, and therefore, of course, the rotor resistance, the bar resistances are the same. So the amount of current in each of these bars would be different. And since the induced voltages are sinusoidally distributed, depending upon where these bars are located, the currents would also be sinusoidally distributed in these bars over here. So you can see that any bar has this current, which is given by the voltage induced in that bar divided by R bar. So we get this expression here, assuming that the rotor leakage is negligible, which is quite often the case for under the conditions these machines operate. All right, so let's see what happens. When we have currents in the rotor bars, they produce their own MMF. So this BMS was produced by the magnetizing currents that were drawn from the voltages applied to the stator, and in response to, which is of course rotating at omega sync, but in response to that, they are induced voltages in the rotor bars, which are, maximum here and here, and cosinusoidally distributed. Similarly, there are bar currents. So these bar currents also are cosinusoidally distributed, highest in these two, as shown here, coming out here and going in here, and then the bar currents drop off as you move away from this axis. So even though the rotor bar cross section in each of these bars is the same, these are drawn by different size circles to indicate that rotor bars are actually different, and therefore we have this sinusoidal distribution of currents, and which results in an MMF or flux, and and we can apply space vectors because these are sinusoidally distributed. So this is the flux density distribution representation produced by the magnetizing currents drawn from the stator. These are the flux produced by the rotor MMF due to the rotor bar currents. But like we agreed, just like in a transformer, the net flux here through the air gap cannot change if you ignore the rotor resistance, the stator resistance and the stator leakage inductance. So additional currents have to be drawn from the stator side to produce an MMF and flux, which nullifies this flux, which is produced by the rotor bars. Okay, and that's how stator of this machine knows that something is going on on the rotor. So we can represent all this by a space vector diagram. We have this at some time 0. Let's say voltage A is peaking, so Vs is along A axis. The flux density space vector is over here. The magnetizing current space vector is over here. The MMF produced by the rotor bar currents is shown here, which is nullified by equal and opposite MMF due to the additional currents drawn from the stator, which we'll call Fr prime. And this is the currents that are additional to the magnetizing currents that are drawn from the stator side. Let's call them IR prime. So the total current drawn from the stator phases can be represented by the space vector, which is the vector sum of IR prime and IMS over here. So this vector over here. Okay, and of course the current those are drawn depend upon how much is the peak flux density here, and also the slip speed. Okay, so it's very important to recognize that the amplitude of these currents is proportional to slip speed. All right, so that's the space vector diagram. And so just to recapitulate recall some of the things here, we see that the slip is, there's a quantity called slip defined, which is the ratio of slip speed to synchronous speed. The slip speed is the difference between the synchronous speed and the mechanical speed, omega m. And if you divide that by omega sync, you get slip. And the slip generally in most induction machines is very low, between 1 to 3% of the synchronous speed. And similarly, the frequency of voltages and currents are at this slip frequency, SF, S times F. So F is the frequency of the voltages and currents in the stator circuit, and so in the rotor circuit, the voltages and currents are that frequency times the slip, which is very small. So in the rotor circuit, the currents are very low frequency, that like 1 to 3 hertz, like that here. And the main thing to notice is that what is happening is that all these space vectors that we saw in the earlier diagram, they rotate at omega sync, okay? Whereas with respect to the rotor, the rotor space vectors are rotating at a much smaller speed, omega slip. But recognize that the rotor itself is rotating at speed omega sub m. So the sum of these two in steady state must be equal to omega sinc. So all these vectors end up rotating at omega sinc. So this is something very important to recognize for induction motor operation. And we can also calculate the torque because we have this magnetizing flux that was produced here. And then to nullify the rotor MMF, this IR prime space vector is drawn, which can be represented physically. Physical interpretation could be through this hypothetical winding. And there's a torque produced on this hypothetical winding, which will be in the clockwise direction, as you can see, but equal and opposite torque is produced in the rotor, which will be in a counterclockwise direction here. And that's in the motoring mode. This is also the speed of rotational direction here at speed omega m here. So we can actually calculate using the principle we have used earlier in case of PMAC machines what the torque produced is. And you can see that it is proportional to the square of the flux density peak and proportional to omega slip here, where omega slip is the synchronous speed minus the mechanical speed of the rotor. Okay, so that's, we can represent this torque speed characteristic for induction machines. Quite often it's shown this way, but if you want to put torque on the horizontal axis, this torque speed characteristic would look like this. But let's look at it this way, that, so omega m is being plotted here. When omega m is equal to the synchronous speed, there's no torque produced here, zero. But as the induction machine slows down, this omega slip becomes larger, and as omega slip becomes larger, more torque is produced. So that's basically and these curves are very linear up to this Tm rated over here, where it's reasonable to assume that the assumption of neglecting the rotor leakage inductance is quite valid. Okay, so, trying to recall how these induction machines operate, if they're running at certain load and they're running at certain slip speed, if you increase the load, so if let's say load torque increases, then what will happen that the machine speed would come down. That means omega slip would go up. That means the voltage induced these bars would go up. That means the current induced in these bars would go up, and therefore the torque produced in these bars would go up. And eventually this torque produced at some lower speed would equal the load torque. Okay, so the operating point, which may be over here at certain speed here, may move to this torque over here and slightly lower speed. Okay. So it brings us to the conclusion of this module, where we saw the operating principle of induction machines, how the voltages are induced in rotor bars, how currents flow in the rotor bars, and how the torque is produced. At certain speed here may move to this torque over here and slightly lower. So in this module, we will look at how we can operate these induction machine drives in a generator mode as a generator. We'll also look at the effect of including rotor leakage inductances as well as the stator leakage inductance and the resistance that we had neglected early on. And we also look at per phase equivalent circuit that can be of significant value, and also determining the equivalent circuit parameters. So let's see how this induction machine, which we have seen earlier in a motoring mode, can become a generator. So let's say that this machine is being driven, is supplied from the stator side with voltages which produce this magnetic field distribution in the air gap to rotate at the synchronous speed based on the frequency which is applied to the stator windings. Now, through a prime mover, this rotor of the machine is being rotated at a speed omega sub m, which is greater than the synchronous speed here. So in this case, omega slip, which we had defined earlier as omega sync minus omega m, that becomes negative. So that's the case being represented here. And as you can see here, once again, the bars which are under the maximum flux density at this instant of time, for example, would have the highest induced voltage. And if you neglect the leakage inductances in the rotor circuit, the highest current. But this time, the rotor bars are moving faster than the speed of this flux density distribution in the air gap. Therefore, the polarities of voltages induced in these rotor bars are opposite to what they were in the motoring case, and therefore the currents are also in of opposite direction. And therefore, the rotor produced MMF, which used to be from right to left, is from left to right, as shown here. And as we had argued early on, that additional currents have to be drawn from the stator side to nullify this, to create this nullifying MMF FR prime. It's also in the opposite direction as compared to in the motoring mode, and therefore the electromagnetic torque that is produced is clockwise, whereas the speed of rotation is counterclockwise. So that's a classic generation mode here, and it shows how these machines can seamlessly go from motoring to generating mode. Now let's look at the effect of including the rotor leakage inductance. It is always there, but initially in our discussion we had neglected them, and it's okay to neglect them when the slip speed is very small, but in general they cannot be neglected. And also if you want to do very precise control, then again these rotor leakage inductances ought to be taken into account. So let's take this case here where we do have rotor leakage inductances. And at this instant of time, for applied voltages, let's say that this B vector, the flux density vector, is pointing downwards as shown here. Therefore, these two bars, one right on the top and one right at the bottom, should have the maximum voltages induced. But because the rotor effect, the currents are lagging, and therefore the currents are maximum in bars which were cut early on. So as you can see, this bar here and this bar here has the maximum current, and as a consequence, the rotor MMF, which was horizontal, in the absence of this rotor leakage, is now at this power factor angle theta sub r, as shown over here. So once again, this MMF has to be nullified by additional currents drawn from the stator, creating this MMF FR prime, and these additional currents drawn are represented by IR prime over here. And if you go back to our discussion, without the rotor leakage inductances, this IR prime space vector was in phase with the voltage space vector, which is not the case here. Okay, so this is shown by means of space vector diagrams in this diagram on the left. On the right, what you see here is that we have because of the rotor MMF, we have two types of fluxes. One is the magnetizing flux, which is over here, And so let's see, I want to point to the right one, this one here, which is crossing the air gap and linking the stator winding. And then there's a leakage flux, which does not link the stator winding. It's just only in this air gap. So what the machine has to do is to, in order to keep the MMF or the flux density vector here the same, additional currents are drawn to nullify this flux by drawing additional currents by the stator windings and creating this MMF, which is shown by this hypothetical winding over here, and creating this flux, which nullifies this flux over here. The stator windings are not even aware of this leakage flux here, so they are only nullifying the flux coming from the rotor, which is crossing the air gap due to this rotor MMF. So that is what's shown here, is that we have this stator flux density space vector created by applying the stator voltages, which draws these magnetizing current. In addition, we have this rotor leakage flux, and vectorial sum of that gives us this BR, which is the net rotor flux, which is cutting the rotor bars here. Okay, and we also see here this rotor produced MMF at some angle, and similarly the MMF which nullifies this rotor produced MMF, and also IR prime space vector here. So things are not at 90 degrees as we had seen before without the rotor leakage inductances, rather they are displaced. So the effect is that the leakage inductances, they reduce electromagnetic torque that is produced. And the effect of rotor leakage inductances really shows up at high slip speeds. So at very low slip speeds, it's somewhat negligible, and that's what we had seen earlier. So what is the per phase equivalent circuit for these machines, including the rotor leakage inductance? We are still assuming that the stator has no resistance and no leakage inductances. So here you can see that we have this space vector diagram on the left, and corresponding to that on the right, we have the phasor diagram. For phase A, we have applied voltage VA along the horizontal axis. Then the magnetizing current is perpendicular to that, lagging behind by 90 degrees. And then IRA prime is the additional current drawn by phase A, and the phasor sum of those two, or vector sum, is the total current IA. So as you can see that this phasor diagram can be represented by an equivalent circuit that is shown in the middle, where you're applying this voltage VA, and IMA is due to this magnetizing inductance, which is causing this current, which is 90 degrees lagging behind the voltage, and IRA prime at some angle is due to this rotor branch, which consists of an inductance and a resistance here. And we can show, and this is done in detail in the textbook. I'll not go into the details here, but this equivalent resistance is given by this expression, RR prime times the omega sinc over omega slip, and this inductance is same as the leakage inductance of the rotor seen from the stator side. So you can see here that this resistance that we have in this equivalent circuit, it depends upon omega slip. Okay, for a given synchronous speed, it depends upon omega slip, and omega slip is in the denominator here in this expression. Okay, so what we can do is we can split this resistance in the equivalent circuit that we had seen earlier into two parts, because the power crossing the air gap from the stator to the rotor is what's going into this resistance in the equivalent circuit on the left, but there's certain amount of power loss in the resistance because of I squared R power loss. So we could call that as the rotor power loss, and we can split this resistance in two parts, RR prime, and whatever is left is the resistance, which is then the power into it in this fictitious resistance, if you will, is what is converted into electromechanical power going into the shaft here. So you can see here that we want to again keep this omega slip as small as possible. So the amount of power lost in the rotor circuit would be as small as possible. So next thing we need to do is to include the stator resistance and stator leakage inductance, which is done here in this equivalent circuit. And we just need to modify the per phase diagram we had by including the drop across the resistance of the stator and the resistance of the inductance as shown here. And that gives us what the net applied voltage ought to be. Or if the applied voltage is given, then knowing the condition under which this motor is operating, how much load there is, we can calculate the rest of the quantities. Now we look at how we can get the parameters of this motor equivalent circuit. We can by DC measurements, we can find out the rotor resistance here, R sub S, and we'll do a no load test that will give us the magnetizing inductance, and also a block rotor test which will give us the rest. So let's take a look here. Of course, you can measure the DC by DC measurement the stator resistance, but if you have no load on the rotor connected to the rotor and you apply a certain voltage, the machine would run pretty close to the synchronous speed, its synchronous speed, and therefore we can assume that the current in the rotor branch is essentially zero, and we are left with this approximate circuit shown on the right. And here the magnetizing inductance is usually quite large, so we can ignore the effect of stator resistance and stator leakage inductance. And therefore, this experiment here, by measuring the applied voltage and the current drawn, we can calculate at least approximately what this magnetizing inductance would be. Now, the other test we can do is the block rotor test, where we can completely block the rotor and apply some small voltage so that the current drawn does not exceed the rated current. And if you see this circuit on the left here with rotor blocked, omega sink is the same as omega slip rather is the same as omega sink under that condition. So in the figure on the right, you can see that all we are left with in the rotor branch, as far as resistance goes, is RR prime, and that's a pretty small value, and the leakage inductance is small as well. So essentially, the rotor branch ends up shorting out the magnetizing inductance. So that can be neglected, and that implies that in this circuit, we can assume that the magnetizing current is quite small. So approximately speaking, the magnetizing inductance is ignored as are considered open circuit here. So we are left with the circuit on the right, and there we can, by measurements and making certain approximation, that the stator leakage is 2/3 times the rotor leakage. It may vary from the machine class to machine class. We can determine the remaining parameters here. So this brings us to the summary, where we have seen how an induction machine can operate as a generator, and what the effect of including the rotor leakage inductance is would be. We have seen the per phase equivalent circuit, how we can derive it, and how we can get the circuit parameters.
Before we proceed with the next session, which will where we'll be talking about controller design, we'll be continuing with a little bit more on induction motor, and then finally about PI controller design to do speed control. Let me just briefly go over some of the parameter estimation that Professor was talking about in the no-load test and the block rotor test. This is quite essential to get the parameters right to be able to design the controller that we shall be doing later in the afternoon session. So as Professor mentioned, so the parameters that we need to know for the induction motor to be able to design the controller in the equivalent circuit is, of course, the stator resistance and the rotor resistance, and then the leakage inductances, both the stator leakage inductance and the rotor leakage inductance, and then the magnetizing inductance LM. In addition to this, we would also require the knowledge of inertia of the coupled system, and if available, the frictional coefficient as the viscous frictional coefficient as well as the static friction coefficient, if these are available. If it is not, we can very well ignore these to be zero and still design the system with just the knowledge of inertia. So as mentioned, to estimate the resistance, all we have to do is do a multimeter, take a multimeter to your stator with the rotor not rotating and measure the resistance across it. That would directly give you the stator resistance. And when you want to measure the impedance, LM, you can so do the no-load test where you apply a rated voltage across your stator winding and let your rotor rotate without any load, which would essentially make the rotor look as if it's open circuited, because your S in this diagram starts to tend, the slip tends towards zero at open load. And so, or if you have a DC motor connected to emulate a load, the best case scenario would be to run this, apply a synchronous frequency. Say if it's a 60 Hertz motor, apply, if it's a 60 Hertz motor, apply 60 Hertz frequency on the stator, and then rotate the DC motor in speed control so that the shaft rotates at synchronous speed as well. That would make the slip exactly zero, and this component would become infinite. So the rotor circuit would be ideally open circuited. If a coupled DC motor is not coupled DC motor is not available, and you just have an induction motor, you can still run it at no load. The slip would be really small value, not zero, which is ideally preferred, but it'll be really small value. Still, the rotor circuit can be ignored. So once you know RS and you apply a line frequency rated voltage, you can measure the current, and from the current's magnitude and the phase angle, you should be able to estimate the sum of LM plus LLS. Now, as a thumb rule, like LLS in most motors would be less than 1/4, or way lesser, actually even 1/10 of the magnetizing inductance. So the sum of LLS plus LM can be just assumed to be purely LM, and that would give us your magnetizing inductance. So that will be the no load test that you would do to estimate your magnetizing inductance. And to estimate the rotor resistance as well as the leakage inductance, you would have to load your rotor completely. So which basically means to block your rotor. This could again be done with some mechanical apparatus, or if you have a DC system coupled to it, you can add a full load or set the DC motor speed control reference to zero, which would basically lock the rotor of the coupled system. And then you apply a very small voltage in the V by F ratio. So the block rotor test, one of the important things that you need to note is that you can't apply the rated voltage at rated frequency as you did for open no load test, because if you do that, since it's a block rotor test, there's going to be significantly a huge amount of current that's going to end up burning your motor. Now again, an induction motor can take up to like 7 times its rated current, but that's only during the transient, during start turn on. A block rotor test is for like a little bit of more time than a transient condition. So you would end up essentially burning the windings. So what you would usually do is apply a really small voltage such that the current in the motor equals to the rated current. And the frequency needs to be such that the V by F ratio of this applied voltage is same as it would be in the rated condition. That essentially ensures that the flux in the motor is what it would be in the rated condition operation. So because it's important because the inductance parameter of a motor starts to vary as a function of flux. Since the flux curve is not B versus H curve is not linear, the inductance actually starts to drop as your current in the motor starts increasing, or I should say the flux in the motor starts increasing. So you would apply a small voltage and the small frequency and log the rotor. And in this case, the rotor circuit impedance would be small compared to your magnetizing impedance. So the parallel of the two circuits, you can just assume is purely the rotor circuit impedance alone and ignore the magnetizing. And you already know RS by just measuring with a multimeter. So from the current and the phase angle, you can again estimate what RR is, RR prime is, and what the sum of stator leakage inductance and the reflected rotor leakage inductance is. So there is no good method of resolving. Once you get the combined sum of these impedance, there is no good method of resolving LLS and LLR separately. So it's usually a thumb rule where we take LLS to be 2/5 of the combined impedance and the LLR to be 3/5. Again, this is just a thumb rule. If you look at a lot of other papers, they would recommend some other different ratio, like 4/5, and or 1/5. So the ratios are completely a thumb rule, and you just kind of go ahead with practice based on what the motor size is and stuff. So that is the electrical parameter estimation for the motor. And it's really essential that we estimate these parameters precisely. If not, your PI controller that you design would not give you the desired response. And in worst case, if your parameter varies significantly, your system could be thrown into instability because the controller that you design is stable only for certain operating conditions. And if you were to significantly alter your parameters, or if the motor's parameter were to significantly be different from what you estimated, the whole stability would be altered as well. And so the important thing to notice is as the motor keeps rotating, as the motor keeps running, the resistance are going to heat up, and that is going to cause the resistance to change in the motor. And this parameter change again needs to be accounted for if you're designing any controller that's expected to run on a motor for a long period of time. And usually people kind of solve this by designing a controller which can operate under a huge range of parameter differences, or the alternative would be to dynamically keep estimating the parameter as the motor keeps running. Going ahead, how to estimate the mechanical parameters. So you have three parameters that needs to be estimated, which is the inertia of this coupled system, and then the viscous friction coefficient, which is B in the diagram here, and then the static friction TC. The static friction coefficient does not come in your PA controller design because PA controller usually operates on a linear system. So this parameter is not of any importance to us. It'll just be ignored as noise in our linearized control system design. But the J and the B component are necessary to proceed with the design. So the way you would estimate J is basically you would run your motor to some particular speed and then completely disable the whole inverter. Now this is not same as making the freewheeling, because freewheeling would actively start draining out your energy from the motor. So you just want to completely open it out so that the motor slowly goes to its zero speed. And what you would do is then look at any particular instant, at the time at which you disabled your inverter, what the speed was, take a small time step, and then notice the drop in speed. And from this, you'll be able to get what your J d omega dt is. So this is basically the d omega value that you would measure from your scope, the speed group, and then your dt time, a small step time that you can choose whatever interval. But you need to make sure that the interval that you choose, the speed looks more or less linear. See, if you pick a really long step time, your speed response is not going to be linear in that, it's not going to fall linearly in that step time. So it needs to be really small so that the assumption is valid. And once you have both your d omega and dt, you can estimate your inertia by basically knowing what your electromagnetic torque was at the instant that you turned off, divided by d omega by dt that you got from your graph. And again, to get your electromagnetic torque, you can look at what the measured peak currents were in all the three phases. Look at the three phases and find out whatever the peak current of any of the phase was. And from that, using formulas that are detailed in the textbook, you can estimate what the electromagnetic torque is at the instant that the motor was turned off and the inverter was turned off, and you'll be able to estimate the J parameter. And again, to estimate the frictional coefficient, you take multiple values of it at the moment that you turn off, and you'll be able to plot a linear chart, which would then give you the B frictional slope of the curve would be B, and then the point where the line intersects your y-axis would be your static friction TC. So that's how you would go ahead with estimating the parameters. And as I mentioned, this is quite important, as we would see later in our control system design. These parameters play a crucial role on what your KPKI values are going to be to get desired performance. So with that, before we break for lunch at around 11:20, 11:30, I would like to show a simulation of an induction motor in open loop without any controller, just it's operating. So let me. So hope everybody can see this. So similar to the model that we saw before, where it was a permanent magnet motor that was modeled, again, we would be going in detail as to how to model the system later in the day tomorrow. But for now, let's just assume that we have an induction motor which is modeled, and let's not worry about how to go design this. Let's just take it as a black box. In the previous simulation that we saw, it was a permanent magnet motor which was in closed loop speed control using hysteretic current controller. In this case, it's an open loop induction motor, and we would see what would happen if you add a load onto an induction motor. In a permanent magnet motor, if it's operating under open loop condition and you add certain load, if it is within the rated load condition, the speed would not change. There would be a temporary oscillation, but the speed would always come back to the synchronous speed. Worst case scenario, if your load angle exceeds 90 degrees, which is the point where the torque generated by electromagnetic torque generated by the motor currents is not sufficient enough to satisfy the load torque plus the frictional torque, your motor would come to a complete halt. It would just desynchronize and stop, and then that would cause huge amount of short circuit current to flow in the motor, potentially damaging it. So that's what would happen in a permanent magnet motor if you had to add a load, and as long as the load is within the rated load condition and your voltage is within the rated, if your voltage applied is rated voltage, the current would generate sufficiently so that the torque are always balanced and the speed settles to synchronous speed. But in an induction motor, if you apply a load, the speed of the motor is not going to be synchronous speed. Even if you don't apply a load, the speed is not going to be synchronous speed because there's always some frictional loss element which always contributes to having some amount of slip in the induction motor. There is no even ideally, if you make the slip zero, the induction motor operation would completely break down. It's just not a possibility within its scope. So there will always be a slip, and as you see, once you start adding load, unlike a synchronous motor, the speed of the induction motor starts dropping. So in this model, what we are basically doing is we have an induction motor which is being run with a constant three-phase voltage, and we are applying a load torque, a very small load torque. This was designed for a really small motor. So we apply like around 50 millinewton meter, and at 1 second step time. And you can see at 1 second, the speed just drops. So what we would be doing later in this afternoon is design a controller to ensure that the speed remains stable at the reference speed, even when we add a load. This kind of dropping, the speed should not start dropping. So the other curve that we can take a look at is the stator current of the induction motor. So as soon as you apply a three-phase voltage onto the induction motor, you would see a huge amount of inrush current. So in this particular motor, the inrush current is very limited because we are applying a really small voltage, pre-calculated voltage to not damage the motor. But in an practical induction motor that you would be able to that are used in a lot of industries, the inrush current would be close to around 7 times the actual rated current. So there would be a huge amount of inrush current, and most of the induction motors are made to handle that kind of transient current condition initially, at least. The reason for this is initially when your rotor is not rotating, the slip is equal to 0. So that's pretty much, sorry, the slip is equal to 1. That is pretty much same as short circuit condition, right? That's the block rotor test that we were talking about initially. So when you apply a full rated voltage on a short circuited motor, you're basically going to, there is nothing preventing, there is no back EMF that is being induced to reduce the amount of current that's drawn. And that's the reason you see a huge amount of current. And then the current starts slowly settling down as the motor starts rotating faster and faster and approaches closer to synchronous speed. And that's what you see, like the speed starts to slowly settle down. And once you apply a mechanical load, as we did at time 1 second when the speed dropped, the stator current increases to account for the added load. And that's what happens here. You see the stator current starts to increase. The other waveform that's of quite interest is the rotor currents. If you look at the stator current, they're always at the applied voltage, the frequency of the applied voltage. In this case, I think it was set at 60 hertz. So irrespective of whether it's at start or whether it's at after load condition, once it settles, the frequency would always settle down to the synchronous, the applied voltage frequency. But the rotor's frequency would settle down to your slip frequency. So initially, when the rotor is not rotating, the induced voltage on the rotor would be the same frequency as the applied voltage on the stator, because it's a simple transformer operating condition, right? So since the rotor is not rotating, it's just a transformer which is coupled the stator and the rotor. So if you see, the frequency is exactly 60 hertz, similar to whatever you got in your stator. And once the motor starts rotating, as the slip starts to reduce, as the rotor keeps rotating, this frequency induced on the frequency of the induced voltage on the rotor would also start to die down. And at no load, the slip almost goes to 0, and you see the frequency almost go to 0 as well. So if the slip were to go to 0, the voltages on the DC, rotor would end up being essentially DC, which again is not a possibility, but just for consideration. And once you start adding load, the slip would start increasing, the rotor slip, as the speed reduces, and you can see there is more voltage that's being induced, both in magnitude as well as frequency. The induced voltage starts to increase. Again, as I mentioned before, we will be going in detail over how to design this model later tomorrow. And when we get back from lunch at around 1:30, we shall continue with induction motor operation, and then look into designing a controller to ensure that the speed of an induction motor as well as a permanent magnet motor remains a constant irrespective of what load condition you put the motor through. So with that, we shall stop this session, and let's get back together at 1:30 sharp. Thank you. Welcome back, everybody. We will be starting in about 2 to 3 minutes. We'll just wait for other people to join as well. In the meantime, if any of you have any questions, post them in the chat, and I'll try to reply to them as best as I can. So let's continue with the remaining 2 videos on induction motor operation. And after that, we will look into PI controller design for controlling a DC motor. And the same principle will be extended to design of a controller for induction motor as well, which we will see later tomorrow. And after that, we will look at the new lab that we have created for both the basic electric drives and the advanced electric drives. And this should hopefully be like a short session between 1 to 2 hours. And yeah, if you have any questions in between, just post them in the chat, and I'll get to them as soon as possible. All right.
In this module, we will look at operation of induction machines directly fed from the line. That is, by and large, there is no power electronics, and you are just directly plugging these motors across the line. So let's look at these characteristics here. The torque speed characteristic on the left shows that this machine has a fairly linear torque speed characteristic close to the synchronous speed. And but as we move away from the synchronous speed, when we put more and more load onto this machine would slow down, and the speed would decrease. So at that time, what happens is that we have the effect of rotor leakage inductances, which becomes quite significant, and also the drop across the stereo resistance. So this torque speed characteristic, rather than remaining linear, it begins to bend over, and we reach a certain point where it's called the pull-out torque, and beyond that, it's kind of an unstable region, and this is the condition we have at the starting point, where we have this much torque available when the speed is 0. And we'll see that later on as well. And also on the right, then we have this rotor branch current as a function of the rated current. When it's operating under its rated condition, that means at rated torque and rated voltage at rated frequency. And you can see that this induction machine at startup may draw 6 to 8 times the rated current. So let's look at its performance in terms of efficiency, power factor, and the motor currents. We can see that these things are optimized near the rated load condition, 100%, where we have the maximum efficiency and fairly high power factor and a certain amount of current. But as the load is reduced, the efficiency can begin to go down and can become very poor under very low load conditions. And similarly, the power factor. Now, when we start this machine directly from the line, what happens is, as I mentioned earlier, the current can be 6 to 8 times the rated current, but the torque that is produced is somewhere here at 0 speed. So the torque produced is what is called T start, and the load torque is shown dotted here in the figure on the right. So the difference between the electromagnetic torque that is produced by the machine and the load torque, that's the accelerating torque, and that accelerates the machine to the rated point as shown here in the figure on the right here. Okay, so it takes a while before the machine, it may be a few seconds, the machine would come to its rated operating point, or the steady state operating point, I should say, and also you can see that the currents would come down as shown in the figure on the left. So we have all experienced that when these line-fed induction machines, when they start, because the large currents they draw, the lights tend to dim because of the voltage drop. We can avoid this type of large starting currents by having a soft start circuit here made up of back-to-back thyristors, and it's quite commonly used in general purpose induction motor drives, but use of power electronics where we are trying to adjust the speed of these machines in a more efficient way, we do not need this soft start mechanism here. The whole idea here is that we can, by these back-to-back connected thyristors, we apply a smaller voltage across these machines at start, and then we can keep increasing these voltages being applied as the speed comes up. So as a summary, we have seen the characteristics of these line-fed machines, and also we have seen what happens under line start and what we can do to minimize these large currents by soft start. So in this module, we will see how we can control the speed of these induction machine drives, not just motors, but also in the as a generator here. But although we'll talk mostly in terms of motors, but certainly it should apply to generators. So here's the block diagram that we have, and we can see that we have a power coming from the line, and then we have a power processing unit, and then this dotted lines that you see in the sensors, they may or may not be there, but even without them, we should be able to adjust the speed of these drives here in an energy efficient manner. Okay. So if you look at the rotor losses, first of all, the power crossing the air gap is the torque times the synchronous speed, and then power delivered to the rotor is at the shaft, not the rotor, but to the shaft, from the rotor to the load or to the shaft, is the electromagnetic torque times the rotational speed, omega m. So the difference of these two gets lost in the rotor resistance, and that's electromagnetic torque times omega slip, and therefore our aim should be to operate these machines at as small a slip speed as possible. And so we can see how this can be done. And so here are some plots here. We have to supply certain torque, T sub L, and at certain speed omega sub m, but depending upon the maximum flux density in the air gap, you can see that we have different characteristics. So as this flux density is increasing, we can see that the slip at which this machine would operate becomes smaller and smaller. So under the omega sync 3 and with higher flux density, we see that we have the smallest slip. So the moral of this slide, if you will, is that we should operate at the rated flux density in the machine. Of course, we cannot go beyond the rated, otherwise the machine would saturate. But certainly, we should be operating at the maximum flux density. So let's look at the torque speed characteristics here with this flux density assumed to be at its rated. And you can see that for different frequencies then, we have different torque speed characteristics where F1 is smaller than F rated and F2 is smaller than F1 and so on. And we can see that these frequencies then give us different synchronous speeds along the vertical axis. They are listed, and if, for example, the load torque that we are supplying is constant, and that's shown by a vertical line in the figure on the right, then you can see that by adjusting the frequency of applied voltages, we can adjust the speed. So at F rated, this machine would operate at omega m rated. At F1, it will operate at speed omega m1. And in this case, where the load torque is constant, keeping this flux density at its peak, the slip speed under all these operating conditions is the same. That is, omega slip 1 is the same as omega slip rated and the same as omega slip 2. Now, let's see what we have to do to maintain this flux density at its maximum value. So let's look at the circuit on the left here, which is the complete equivalent circuit that we had derived in an earlier module, and we can see that if we keep the slip speed small, then this in the rotor branch, the resistive part dominates the inductive part, and therefore it is reasonable to assume that we can neglect that as shown on the right. And so it's what we have then is if you draw the phasor diagram of the circuit and take this EMA as the reference phasor, we'll see that the rotor branch current is in phase with that IRA prime as shown here, and the magnetizing current drawn is 90 degrees lagging behind. And then we can add the drops across the stator resistance and stator leakage inductance due to these two components of the current IA, and IA is of course made up of IRA prime and IMA. So all those are shown, phasors are shown over here. So and the resultant is the applied voltage VA phasor. So the moral of the story here is that as far as the magnitude is concerned, we don't need to worry about the perpendicular part because that doesn't really change the amplitude very much. So we just need to take into account the horizontal part. And so what that says is that we can actually, if you look through the material in the book, that in order to keep the flux density at its rated value as an approximation, we can do so by keeping volts per hertz. The applied voltage divided by the frequency at which it's applied is constant. So that's a fairly, at least it's a first order approximation. But if you want to be more careful, then what we can conclude here is that V over F would give us a straight line going to the origin shown by the dotted line over here. But in addition, we need to add the drop across the stator resistance. And that depends upon the load on the machine and therefore IRA prime as shown here. So to be to be more careful and to actually get this flux density to come out to be at its rated value, the characteristic is shown by the solid line here. And you see that at the rated torque, we need to apply certain voltage boost in comparison to or in addition to what V over F type control would suggest. So here's a summary where we have seen the block diagram of speed control. We have looked at rotor losses and how we can minimize the slip speed by keeping the flux density at its rated value. And what do we have to do to get that condition, and which is approximately speaking V over F control, but we can include the drop across the stator resistance.
In the following two videos, we'll be looking at designing the PI controller for a DC motor. But as mentioned earlier, the same principle would be extended in tomorrow's lectures for induction motor and PMAC vector controller design.
In this module, we will look at designing feedback controllers. In this module, we will look at designing feedback controllers for motor drives. We will look at the objective, definitions, cascaded control, steps in design, average representation of power processing unit, and we will take DC motor drive as an example, though these can be applied to any type of motor drive, and also a structure of PI controller, which we'll use later on. So let's begin with the objective. The block diagram looks like this. We have a desired reference signal against which we compare this output, and the error between these two acts on this error amplifier that we have to design, and it goes to the system that we have. This error amplifier acts on the power processing unit, which in turn acts on this electric machine, which is acting on this mechanical system, and here is our output here. So why do we use feedback? Well, it makes the system insensitive to disturbances and parameter variations. And what are the common control objectives? These are motherhood and apple pie type statements, zero steady state error that we want. We want good dynamic response. It should be fast with not much overshoot. So if you look at the structure, this is what the desired or the reference signal is. This is what we get, and the error between these two is acting on this controller with this transfer function which we have to design, and this is the plant transfer function here. All right, so what are the definitions? We talk about this open loop which includes the product of the controller transfer function yet to be designed and the planned transfer function. And the closed loop response that we are really after can be represented in this, in this form here in terms of the open loop here. So, but we design it, by basing it on open loop here. So in the open loop transfer function, where the magnitude of that transfer function crosses 0 dB, that is called the crossover frequency in hertz or in radians per second here. And then we have a gain margin, but we mostly will deal with phase margin over here. Phase margin is where the phase of this open loop transfer function is with respect to minus 180. So this is the phase margin over here at the crossover frequency. So this is the crossover frequency f sub c over here. All right, and so that's what we are basing it on. And in order for closed loop bandwidth to be as high as possible, we would like this crossover frequency to be high. And that will give us a fast response. So what we generally have in drives is this cascaded control, where the innermost loop is the torque loop, which should be the fastest. And then, so this is the torque current loop here and right here. And then outside of that, we have the speed loop, which is somewhat slower than the torque loop. And then we have the position loop on the outside, if there is a position loop, if you're trying to control position. It's not always the case. Then it's the most outermost and the slowest loop. So what are the steps in designing the controller? First of all, we assume the system is linear about the steady state operating point, and we design the controller using linear control theory. So this is very simple description that we are dealing with here. And then for large signal oscillations, we ought to simulate the system and tweak the controller as necessary, because under large signal, large changes, the system may hit the limit and it is not really linear, and therefore we need to so-called tweak the controller here. So we will take the system and assume it to be in steady state, and around that steady state operating point, we are designing this controller for small signal variations here. Okay, so that's and we would like we should respect that this is not really a linear system as such. It is a switch mode system, and so we need to make sure that our highest bandwidth is at least an order of magnitude lower than the switching frequency here. And in designing these controllers, we'll neglect the switching frequency components with this assumption over here. So the very first thing we do is we take the power processing unit, and for a DC motor drive, this is what it will look like. But we use this average representation where we get rid of the switching frequency components. And therefore, when we talk about the output voltage VA, we put a bar on top like this to indicate that we are dealing with the average quantity where the switching frequency information has been taken out. And you can see here that is this average voltage here in this converter would be proportional to this control signal, V sub control or V sub C here. So we have this equation, and they are related by some gain, which we'll call KPWM, and we can express this equation in Laplace form this way and draw it in this form over here. So this we have seen before. So now we will apply this to a DC drive, and so on the electrical side, we have this equation here in terms of quantities where the switching frequency information has been taken out. So the applied voltage here is equal to the back EMF times the drop across the resistance times LDI dt over here. Not times, but plus LDI dt. And the induced back EMF is proportional to the rotational speed times the voltage constant over here. So this equation in Laplace form, we can write it like this, where this di dt is this Laplace operator here shows up because of di dt. So we can write it in this form. And from here we can say that this current is the difference of this and this divided by resistance plus S times LA here. And this induced EMF is proportional to the speed over here. Similarly, the torque that we have is proportional to this current. So we have this equation in Laplace form. And if you include the load torque, then maybe we can put T sub L over here. So we can say that the speed is given by this equation. So it's the electromagnetic torque produced minus the load torque opposing it divided by this S times J EQ, which is the equivalent inertia of the motor and the load. So these are the equations, and these equations then can be represented in this block diagram form, where speed times K sub E is EA, and VA minus EA times this will give us the current from this equation. And if you multiply that by torque constant, it gives the electromagnetic torque. Subtract the load torque from it. The difference between these two is the acceleration torque, which acting on this inertia gives us the speed. So all these equations can be combined into this block diagram form. And then I will use this PI controller later on, because in torque and speed loops, if you want zero steady state error, then we should have an integral control as well. So you can see here, this is the reference, this is the actual, the error between these two. In this controller, we have a proportional path over here, where this is the gain of the proportional controller. And then similarly, this is the gain of the integral controller. So this is the integral part, because we have S in the denominator. And on the top here, we have the proportional controller, and the K sub P is the gain of the proportional controller, and K sub I is the gain of the integral controller. So these two together would be something which we'll call PI controller. So this brings us to the end of this module here, where we looked at why do we use feedback control, what are the definitions of crossover frequency, phase margin, cascaded control, where we have torque control and then speed control and the position control. What are the steps where we assume that we are at some steady state operating point, and for small signal disturbances, the system is linear, we assume, and we'll use linear control theory, and then tweak that controller for large disturbances. And in doing so, we want to get rid of the switching frequency, so we use the average representation of the power processing unit, and we take a DC motor drive as an example, where we will use this PI control. In this module, we'll continue with the controller design, and we will look at design of torque loop, which is the fastest, and then the speed loop, and then the position loop here. So let's look at our system. and we are using DC motor drive as an example. So we have, we are trying to design this torque loop, which is the innermost and the fastest loop here. And so let's say that, torque and current, they are proportional to each other, so it doesn't matter. And so this is our reference current, and this is the actual current, which is being measured, let's say, over here. And so the difference of these two goes into this PI controller, which produces the control voltage, and that times the kPWM, that is the voltage that gets applied to the armature terminals. And from this, we must subtract E sub A, which comes from the speed. So speed times KE is E sub A. So the difference of these two acts on the armature resistance and the inductance, which is expressed in this form. This tau sub E is just the inductance divided by the resistance of the armature. So it just expressed a little differently. So the output of this block is the current, which acting on the torque constant gives us the electromagnetic torque, and subtract that from that the load torque, and the difference between these two acting on the inertia here gives us the speed here. So we have sort of an interleaved loops, I should say, and we want to simplify it to something that we recognize. So for one thing, let's forget about this load torque here in under the steady state operating point. And so what you can see here is that from this point on, this part here, we can represent it like this here. So IA times all these things taken together would give us EA, and that's what we are showing here. But IA also times KT is electromagnetic torque, which acting on inertia gives us the speed here. So we recognize that, but that is really not our concern at this point. So what we will do is we can make another assumption here, that let's say the inertia is quite large, so we can ignore this term here. And if we do that, then the block diagram that we come up with is just this over here. And here you can see that this open loop gain, which is the product of these three blocks. So you have the PI controller, this over here, then kPWM over here, and the motor is represented over here. All right. So to design this thing here, one of the procedures could be that we select the 0 of this PI to cancel the motor pole. And if that happens, then you can see that the ratio of the two gains in the proportional and integral control, they will equal to this electrical time constant tau sub E. And we can then, this open loop then, open loop gain can be expressed like this, where this is given in terms of these other system parameters here. And we can choose this K sub I to achieve the desired crossover frequency to be like this here. So that gives us how to choose these parameters in the torque loop. And then we come to the design of the speed loop, and here we assume that the torque loop is ideal, the current loop is ideal. So whatever is desired is delivered over here. So the gain and the transfer function for the torque loop is really unity, and this is assuming that the speed loop is perhaps an order of magnitude slower than the torque loop. And so in this case, we can then select some reasonable phase margin and come up with a similar arguments, the PI controller of this speed loop here. And then we have this position loop, which is the outside loop, and here we can assume that the speed loop is again an order of magnitude slower, So the speed loop, position loop is an order of magnitude slower than the speed loop. Therefore, the speed loop is really ideal. So whatever is the desired speed that we want is what we get. Then the system is very simple here. We really don't need to use an integral control, and we can come up with the desired crossover frequency and bandwidth. So there are certain other things we should be aware of here, that if we have the information already for the torque that we want, the speed that we want, and the position that we want, so those things can be fed forward, so to speak, as shown here. We also should have the limits, and these limits then produce nonlinearities. So we should be aware of that because, for example, from the power processing unit, the output voltage that we can get cannot exceed plus or minus the DC bus voltage. So that type of things, those limits we must observe. And also when we have integral control, we can have this integration wind up. So we should be aware of that, and that is discussed in this chapter here. So in summary, we have looked at the design of the torque loop, the speed loop, and the position loop.
So in this part of the section, let's look at some simulations again to see the effect of changing the KPKI parameters. And after that, we will look at V by F closed loop speed control of an induction motor before going into a presentation on the controller that we had designed here at the University of Minnesota. So So this is a simple DC motor model. Here you have the voltage and the applied terminal voltage minus the back EMF, which is obtained by multiplying omega m into Ke. And then you subtract that, pass it through 1 by SL plus R. You get your armature current. And then you pass that through KT. You would get your electromagnetic torque. Subtract that from load torque. And the differential torque, you pass it through 1 by Sj plus B, you would get your omega m. So this is a model of an induction DC motor. Is maintain the current of the DC motor at some particular value. That's the control parameter. So our reference is going to be a current. So initially the current is at 0 amp, and we want to step it to 1 amp and maintain it at 1 amp, irrespective of the load condition variation. So the PI controller would take a reference of the first input would be the reference current that we desire, and the feedback input would be the actual DC motor current. And then you have the KPK value, and then integrate it, sum them up, and pass it to the output. That will be your output voltage. So here we are assuming we are linearizing the power processing unit and just assuming it to be a 1:1 block. So we are not modeling that here. And to notice is the saturation block that we have to limit the output voltage. So these are the nonlinearities that were being that was mentioned by Professor Mohan in the previous video. So these nonlinearities affect the performance. We will see how removing this nonlinearity, the performance, how it would be without this, and once we add this nonlinearity, what happens. Even if we remove this in the control, in real-time implementation, it would still be limited because your DC bus voltage has a limit. So this is a practical limit, not just a digital control implementation-wise alone. And in addition to that, as Professor mentioned in the previous video, you would also have a limit on the integrator as well. So you would not want the integrator value to saturate and then continue like the output voltage to saturate and the integrator to keep integrating. If there was no anti-wind-up present, and say if the output voltage the error is so high that the output voltage required is more than what the DC bus can provide, and the integrator keeps integrating to say the DC bus is 40, and the integrator integrates to 40, 50, 60, and keeps going. And the problem is once the error dies down, the integrator would have been all the way up to say 100 or 120 volts, and then you would, as the error goes more and more negative, the voltage would still be positive, which would keep on contributing to the error. So what this would lead to is a limit cycle kind of response. It will eventually damp out, but it would be like a limit cycle kind of response where it keeps on oscillating for a significantly long period of time. And hence you would add an anti-wind-up to prevent that kind of oscillatory performance in your output. So this is the PI control model, and let's run this model and look at the current. Before that, let's look at the speed first. So the speed is not controlled in this model. So it's going to settle at whatever speed your frictional laws determine to be. So the inertia is not going to play a response in the final output speed, because your output speed, the rate at which it increases is going to be dependent on the inertia, but the final steady state value itself is only going to be a function of the viscous friction. So if there was no viscous friction in our model, so when we look at this model here we have an inertia 150 E minus 6 and the viscous friction of 500 E minus 6. If this term was 0, then your output speed for a constant input current would just be a ramp, because it's just 1 by Sj, which is an integral transfer function. So the frictional component limits it. And once we add a load, even though we are maintaining the current constant, once we add the load, the speed is going to drop, because for the same current, if you add an additional load, the current into voltage, the power in is the same, but your power out needs to be the same too. So your load increased, that means your speed needs to decrease. So that's the response that you see here in a speed control. And if you look at the current response, you can see that at 1 second we asked for a current step of 1 ampere, and it goes to 1 ampere and settles there. And we give a load torque at 7 seconds. And let's see, at 7 seconds, there is like a small blip there. If you design a bad enough controller, you can see a good enough oscillation. But if it's a decently done controller design, then the oscillation will be very limited. So it's just like a very small increase in the speed, and then it comes back and settles down again. So of interest is the initial oscillation that you see. So this is an underdamped response that you have here. And we can play around with the kpk values to kind of change this response further and further. For the usual value that's chosen, as mentioned in the video, is for the phase margin to be above 45 degrees. And we'll talk a little bit more about the bandwidth selection later. But yeah, the phase margin usually above 45 degree would give you this kind of underdamped response. And depending on your application, you would choose different kind of response. So if you want a fast response, it would most likely be an underdamped system. But if you want a safer response, say you have a robotic arm, and you definitely do not want an underdamped response in your robotic arm. Say this is the position of the robotic arm, the response. And if you designed an underdamped system, your hand is going to swing around and hit the wall or something. So in a robotic system, you would usually have an overdamped system. So depending on different kind of application, the parameter kpk you would choose would change depending on whether you want an overdamped system or an underdamped system, and the response bandwidth and stuff. So in this case, we are having an underdamped system. Let's change the parameter and see if we can make it a little bit more underdamped. So let's do 10. I'm not sure if this would make it unstable, but let's give it a shot. Oh, so we need to, for this part of the experiment, we need to disable the saturation because the nonlinearity is going to take over and it's going to prevent you from seeing the actual response, that the idealized response that would be present in an actual in the simulation model. So there's a little bit of more added oscillation, if you can notice, when you reduce your Kp value. So let's do instead of 14, 20. And then when you increase your Kp value, you can see your oscillation kind of die down a little bit. So let's do that again. So here you just see like a one peak which goes to about 1.2 ampere and then settle down within like 1 or 2 oscillation, not even 2 oscillation or 1 oscillation. And if you reduce the Kp value, what this basically does is you're increasing the ratio of Ki to Kp. So there is more storage element in your controller compared to your damping or damping element equivalent. So what it basically does is adds more oscillation because your Ki value is much higher compared to your Kp value, because we are not changing the Ki value, so the ratio of Ki to Kp is increasing, and that's the reason you see more oscillation when I reduce the Kp value. So this could be done like I'm just randomly changing here, but these initial value of kpki of 14 and whatever 40,000 was determined by the phase margin of 60 degree and bandwidth of I think it was 600 hertz. So the design procedure is detailed in Professor Mohan's book. You can take a look at that for the steps of getting to the value. And about choosing the bandwidth, so ideally, as mentioned in the slides, you would want a bandwidth which is about an order of magnitude, the inner current loop bandwidth to be an order of magnitude lesser than your switching frequency. So say you have your power processing unit switching at 6 kilohertz, then you would want your in a current controller to be less than 600 hertz. And then if you cascade a current or a torque controller, and then if you cascade a speed loop onto it, you would want that to be 1/10 of it, so around less than 60 hertz. And then if you cascade a position loop on top of the current loop, you would want that to be again 1/10 of it. This 1/10 is just a thumb rule, but you should definitely not exceed 1/2 of it. So if your switching frequency is 6 kilohertz, your current loop shouldn't be greater than 3 kilohertz. The reason for this is there are two ways of looking at it. You can think of your motor model to be a digital to analog converter, because your power processing unit is going to be giving digital output. It's either going to be the DC bus voltage or zero. So it's just a series of on and offs. And what your motor model essentially is, it's a low pass filter. It's going to take this fluctuating voltage and convert it to a nice smooth current or a speed signal, right? So it's a digital to analog converter, just at a higher power level. So, and from digital to analog conversion ADCs, we know that the Nyquist frequency has a limit. Like, anything about 2 times is preferable for replication of the input signal faithfully. If the transformation, if the frequency that's being sampled is less than 2 times the actual input frequency, then the output is going to have components which are not frequency components which are not present in the input. It's going to cause aliasing effect. So that's one way to look at it. So your subsystem or your motor model must operate at least 2 times the frequency of your current loop bandwidth or your power processing unit. So that's the whole idea of switching at least 2 times higher than your bandwidth, and preferably the more the better. So 10 times is a general thumb rule chosen there. The other way of looking at it is if you have your current controller at a frequency, say, higher than your switching frequency. So your current controller bandwidth is 20 kilohertz, but your switching frequency is 10 kilohertz. then your output current is going to have switching frequency components. So in addition to the fundamental, your output current is going to have a component at 10 kilohertz, 20 kilohertz, 30 kilohertz, and all the n multiples of switching frequency. So what your controller now is going to be doing is, in addition to controlling the fundamental component, your reference, it is also going to try and compensate the switching frequency component. So the controller is going to go berserk. It's just not going to be able to figure out a proper operating point because it's looking at the switching frequency component as well and trying to actively compensate for that, which it shouldn't be doing. So both of the reasons are based on the same principle, and that's the reason why we choose like 1/10 as just a thumb rule for every additional loop that you add. The bandwidth needs to be 1/10, or it's preferable if it's 1/10 that of the inner loop's bandwidth. So that is a brief discussion about the PI controller design. And again, as I mentioned, you can find all these resources in Professor Mohan's book. For the next part, what I would like to show you is V/F control of an induction motor, closed loop speed control, and okay. So again, in the previous model that I showed you, we had an induction motor model using DQ, which we shall be going, which we shall learn tomorrow. And in this experiment, it's modeled using ABC reference frame. And again, this will be dealt tomorrow early morning session, where we'll look into how to design an induction motor ABC model. But for now, let's consider it to be a black box again. So what we have here is a speed reference, and then we have a PI controller, which generates the slip speed that needs to be added on to the reference speed so that your induction motor settles at whatever required speed that you need. So there's a little bit different way of doing the control. You can just directly have this PI controller output be proportional to omega sync, but that would kind of affect the performance a little bit. There's kind of like a feed-forward term that makes the performance a little bit better. Again, we will deal with the theory behind this later in tomorrow evening's lab session. If somebody has a question, we can go over it at that point. So what we have here is a reference signal that's generated, the speed that's desired, and then we pass it through a V/F block to determine what voltage needs to be generated. And that voltage, we pass it through an induction motor model, a mathematical model, and then we see if the speed settles down at the desired value. So the PI values are computed here. So we have the transfer function of the induction motor 1 by J plus B, which is the mechanical transfer function. We can assume the inner current loop and the inner power processing unit as 1:1 transformation ratio and ignore that part of it and just design the PI controller KPKI values as explained in the book. So if we run this model, so our goal is initially we need the speed to remain 0 for 1 second, and then it needs to settle at 100 radians per second after 1 second. And we add a load of, let's look at the load value. So we add a load of 20 millinewton meter at 3 seconds. So at 3 seconds, you would probably see like a small dip in the speed, but if the PI controller is designed properly, the speed should recover pretty quickly. So as you can see, at 1 second, the speed starts to ramp up and then settle down at 100. And then at 3 seconds, the speed dips a little bit, but the controller comes back into act. Like it's always in action, but it kind of compensates for it right away. And it settles down back at 100 radians per second. So another note is this kind of ramp response, as I mentioned earlier, and when we showed another version of, when we looked at permanent magnet hysteretic speed control, we had the similar ramp response. This is because of the saturation block that we have here, this one, and as well as the anti-wind-up. So in a simulation model, if both of the anti-wind-up and the saturation was removed, you would have the response look similar to what you would have with a underdamped linear first order system. So it'll be a rapid curve with very small rise time and then a little bit of oscillation and settle. So this ramp is because the voltage is being limited. The controller requires a much higher voltage to be outputted, but the practical limitation of the power processing unit prevents it from achieving a better performance. So you get this kind of limited ramp response. So that's pretty much about the PI controller design for vector control model. If you have any questions regarding the control design or anything, let me know, and I can wait for a couple of minutes to see if anybody has any questions. If not, we will proceed with about the software, and if we have time, we can look into designing, or if anybody is interested, we could look into designing like a simple model using the software. So anybody who's interested into looking at how to design these controllers, you could look at, you can go to this website, cyamble.com. We will be posting a link on CUSP website for this as well. And you should be able to go from there there too. So you can look at if you go to Cyamble website and go to resources, and you have the basic drives lab as well as the advanced drives lab, you can go to whichever. And then we have like whole set of experiments. So the one that we saw just before the last experiment was this one, which is the DC motor speed control. So you have all the procedure as to how to design your PI controller, and step by step, and run the simulation, and then run the hardware as well if you have the hardware with you. And the other experiment that we saw is part of the advanced electric drives, which is induction motor V/F control. Again, the procedure to design the KPKI parameters and the control system, everything is given in detail here that you can just follow and kind of redo the same thing and run the simulations if needed. And the MATLAB simulation, so this is using a different software that we developed that you can download free of cost. But if you prefer to use it in MATLAB, as many people are familiar with MATLAB, the MATLAB files are also available with the book. I think it was like a CD attachment. And if you don't have the attachment, just send Professor Mohan an email and he should be able to send you the files for those. All right, we'll take a 5 to 10 minutes break before we jump to the final session, which would last for like 20 minutes, 20 to 30 minutes. We will look at the lab implementation of induction motor vector control and other simple experiments, DC motor speed control and stuff. So before that, let's take a 5 to 10 minutes break. And if anybody has any questions in the meantime, just post it on the chat and I'll get back to it once we are back from break. Welcome back, everybody. So the final part of this afternoon, I'll be talking about the low-cost real-time prototyping platform that we developed here as part of our ONR-funded project. And this is the Drives Lab that we have been offering in our in the University of Minnesota for the past 2 semesters and past 2 years, and it's been acquired by around 10 to 20 universities so far that have adopted this newer system, in their own teaching laboratories as well. So previously we used to offer, we had designed these electric drives laboratory using these 3-inverter board that you can see on the right, and we used to offer it as part of the basic drives course. It had a lab session with it, and usually around 60 students take the lab sessions and 120 students take the courses. Similarly, we had a power electronics course as well as lab, and that's the board that's shown on the top, the board that we use for our lab. And the one shown on the bottom has three-phase inverters on it to control a defect motor along with a DC generator for loading. So in the previous drive system that was offered for I think around a little over a decade till the last spring, we used to use MATLAB Simulink to do simulation as well as real-time code generation. And then for the real-time laboratory implementation for the controller, we used to use DSpace DS1104. And for the power electronics part of it, we used to use these 3-inverter boards that were designed at the University of Minnesota and were sold by a third-party company called Hyrel Vishay. And they also sold, another company used to sell the 4 motors that used to be used for these labs. And there were 2 DC motors, an induction motor, and a permanent magnet synchronous motor. And all the experiments were carried out using this setup. So this used to be quite expensive. So for the academic version of the combined MATLAB DSpace and the inverter and the motor, each station used to cost about $20,500 upwards of it, and the non-academic was even more expensive. And a lab usually has around 5 stations, so that's $100,000 investment right there to get this lab set up in any university. This put a huge limitation on the number of universities that adopted this because it was really expensive to get this lab up and running. So we wanted to reduce the cost burden on universities so that more number of universities, especially community colleges, which do not have huge funding, could offer these kind of solution. So that a lot more, so that this education material could be more accessible. So with that aim, we developed our own numerical simulation platform, and which has the capability to do real-time code generation as well. And it's called Workbench, and we made it available absolutely free of cost. Anybody can download. Many of the functionalities that you can do is very similar to what you would get with other simulation platforms that are available out there in the market. So you get model-based simulation, you get code-based simulation as well. You could do all of this using this software. And this was designed completely in-house using our own proprietary code. This project was completely funded by the Office of Naval Research for the past 4 years. And the power electronics board that you see in the bottom right corner, we redesigned that as well so that it has an onboard controller in it, so that we wouldn't have any need to go for expensive DSpace. DSpace does sell heavily discounted for academic institution, but that's still $6,000, and that was still a little bit expensive for some of the community colleges that we are targeting, and hence the reason that we added a digital signal processor on board that can be directly controlled from this Workbench software. So you don't need any additional hardware to be able to control this particular inverter module. And the capabilities are similar. It has the same three-phase inverters inside it, and it takes the same 40 volts. The output current is 5 ampere. The inverter itself can take 10 ampere, but just for lab safety, we have limited to 5 ampere. And all of it is contained within the box, and you don't need any additional capabilities. And one of the other limitations that we had when we used to use DSpace was these need to be connected. There needs to be some modification made to your PC hardware to be able to accept this PCI connection to be able to interface with this DSpace hardware. So if students were to use their own laptop, they wouldn't be able to interface with this DSpace system that we had. So the new system that we created, we made it just simple. It was just connects through a USB cable. So any laptop or hardware, any computer running a Windows can directly connect to this hardware and run the laboratory without any additional setup or hardware modifications required. So as I mentioned earlier, Workbench is completely free of cost, available for any individual users. You could, or as well as academic users, any universities can download absolutely free of cost and use them. And there are no license limitations or anything. In the inverter or hardware, the redesign is about $1,300, and including the 4 motors, the total cost comes to $2,700, while previously the inverters and the motor combined came to about $7,500. So a single station right now for any university that needs to adopt this Drives laboratory would be around $2,700. So that's extremely cheap. And even if you had to buy 10 units, that would be lesser cost than what you would have to pay for a single unit in our previous version. So what is Workbench? As I mentioned, it's a numerical simulation software. It's model-based, where you drag and drop blocks, connect them up, and the solver in the backend would automatically solve your model and give you the results. And not all systems can be implemented in model-based. For instance, if you want to do some iterative function or some recursive loops, it's much more easier to program those logics in code rather than in model. It can be done in model, but it's much more easier to do them in code. And not everything is easy in code. If you want to do time-based simulation, like a PA controller or motor model, it's much more easier to do it in model-based rather than code-based. So we offer both environment. You can do model-based simulation, and we offer a code-based simulation as well. Both you can split functions between the two. You can have some element of the program running in code and some element in model. And the code-based programming language is very similar to C++, C#, any object-oriented programming language. So if you're familiar with any of those, you should be quite comfortable with this as well. And the big difference between other object-oriented languages in this is it has inbuilt support for matrix operation. Similar to what you would get with M-File, all the matrix operations can be done within this programming language. You don't have to have any additional libraries or anything added on to it. So how it all started, like it started off as a lab development a little over 3 years or 4 years back. And we wanted to create a cheaper solution for power electronics and motor controls. And the first thing we did was we evaluated all the solutions available off the shelf. And all of them had some shortcoming because of which we couldn't use that particular solution. So on the left, we have Plex, PSIM, Vissim, and MATLAB. All of these were a bit too expensive for the target market that we were aiming. And there are free model-based simulation options out there as well, Scilab, but these were too primitive. Like they generate generic C code that does not interface with any particular controller, which means the students would have to do a lot more programming and stuff, which was not the requisite of the course that we are targeting. So that was not a feasible solution either. And the alternate option is using native programming platforms like Code Composer Studio or MPLAB offered by PIC microcontrollers. But this again requires programming knowledge, and that's not a prerequisite for anybody taking this course. And that would be an undue burden that would prevent them from learning what we intend them to learn. So we developed it at the U of M, as I mentioned earlier. It's currently being used in our graduate lab as well as a research lab. My PhD was done using this software and this hardware, and this was funded by the Office of Naval Research. So here is a brief glimpse of the whole screenshot of the modeling environment. On the right, you have the solution explorer. On the left, you have the property windows. And then in this particular model that you see right here is an induction motor vector control model. On the top, we have the induction motor model. On the bottom, DC motor. We will go into detail of this particular model later tomorrow. But for now, I'm just going to talk a little bit more about the software and its functionality, so that when we use it tomorrow in our session, you'll be a little bit more comfortable with it. So some of the features that this software offers that's not available in other solutions present in the market is one of them is the dynamic compiler. So if you had to make any sort of error, if the students were to do any mistakes in the lab, it would pretty much report them instantaneously. So in this particular case, you see if I delete this link, you'll get a warning immediately saying there is a tool that's not connected. And if you fix it, the warning automatically disappears. So we wanted to have this dynamic functionality because most of the time in the lab, when we do modeling, is spent in debugging what mistakes the students have done. So this would eliminate a lot of errors and would greatly reduce the amount of time that's required to get the system up and running within the allocated time in the lab. So this is the programming environment where previously I showed you the model-based design, and this is the code-based environment. The language was designed from scratch, as I mentioned, to support dynamic compilation that I showed you before. The language is easy to understand. It's written in like a fluent English language, so it's quite intuitive to learn and then start programming right away. And as I mentioned earlier, it has inbuilt matrix operation, all matrix operation, transfer, division, rank of a matrix. All of it is all inbuilt into the programming language, so you don't have to know external libraries or anything to be able to access those elements. So one of the major feature of this software is the ability to generate code from model, real-time C code. So and to transition from simulation to real-time, there needs to be no additional input from the user end. So if you had to use a particular controller that we support, and tomorrow you want to move to another controller that we support, the user does not have to know anything about the controller, about the controller that they want to control. So the code that's generated automatically changes depending on whatever processor that you're going to be using. It'll automatically detect the processor and generate the code specific to it. So again, this eliminates any need of microcontroller programming or any form of C programming knowledge to be able to do these labs. So what I'm going to show you here in this video, in this image is, this is the simulation model. And all you have to do is click the button on the top that's kind of pressed in, the sixth button from the left on the top. And once you press that button, it automatically goes to hardware mode. So, and there is we have an intelligent algorithm running in the background, which automatically determines which elements of your simulation model needs to be programmed in real time. So for instance, in this model, in the center, the one labeled IM motor is the induction motor model. And on the left, you have the whole system, whole control system, your estimator model on the top, and then the DC motor model is in the bottom. And then you have a whole lot of control, again, data acquisition and everything on the right and the left. And once you go into hardware mode, the software automatically knows that the induction motor and the DC motor are going to be used in real time. You have an actual motor, so you don't need to run those models in the real time as well. So it automatically eliminates redundancies and eliminates unnecessary tools in the model so that it can run your real-time code extremely efficiently and produce the results that you would expect. And it programs only the elements that needs to go into your real-time control system. So yeah, as I mentioned, it automatically identifies the code. And so coming back to setting for doing real-time control, we wanted to make the whole software device agnostic. So if you had to go ahead and use a TI controller to program, do some vector control or something, there would be a whole slew of register setting that needs to be done before you can get a single signal inside, or there would be like 20-30 register that needs to be set before you can turn on and turn off a PWM signal or get a interrupt from an overcurrent fault. It requires a significant element of programming. So what we did is we obfuscated all of those elements away in the backend and just gave you simple functionalities that you can click and immediately run the program. So as you can see on the left, if you want to have your switching frequency at 6 kilohertz, all you have to go is go to the PWM settings, set it at 6 kilohertz, and you'd have a 6 kilohertz waveform. And if you want to transition from sawtooth to triangle waveform, you just got to change the waveform. So the register setting depending on the device would automatically be computed in the backend so that the user doesn't have to do any sort of programming. And same thing is extended to ADCs and PWM. So if you had used the DSpace based system that we offered before, you would see that the ADC setting, all you have to do is select an ADC channel, and everything else will be done in the background. So this is a similar functionality where everything is in the backend, and the user just needs to select what channel they want, and the data would be acquired and given to you in your scopes on the software. So we spoke about the software so far, and now let's jump into the hardware element that comes along with it. So this is the 3-inverter board, the redesigned 3-phase 3-inverter board. As you can see, it has a 3-phase inverter, which is right below the heatsink, and each of those inverter has 3 legs within it, and each of those legs can take a DC bus voltage of 42 volts, and the output current can go up to 10 amperes, but we have limited to 5 amperes for lab reasons. And it has all the power processing unit on board, so it does not require anything other than an input of 40 volts. It automatically generates all the required power levels, 12 volts, 5 volts, 3.3, to power the DSP, the 1.9 volts, everything, and the driver circuits. All of it is generated internally. And it has all the current sensors on it to be able to do closed loop current control. And then it has 2 quadrature encoder to acquire the position signal to do position control and speed control. And then it has a DSP on it so that you don't need to use an external controller, external real-time platform such as DSpace or other Typhoon Hill or RTBox. You don't have to use any of those. Just this has its own controller on it. And it has a programmer as well and a data logger. So you do not have any requirement even to buy a DSO, because those can be quite expensive, about $1,000 to $2,000, $3,000 per scope. So we wanted to remove that financial burden as well. So it has an onboard data logger. The data logger is not as good as what you would get with a $3,000 scope, but it's good enough to do drives control and observe the drive results from the electric drives experiments. So everything is contained within the single box. All you need is a USB cable and 40 volts power supply, and you'll be ready to go to control any of the motors within the power range that's mentioned. You can independently control 3 PMAC or induction motor simultaneously. Or the purpose we put 3-phase inverters on board was to be able to control a DFIG. So that would require a 3-phase inverter for the stator, and then a 3-phase inverter for a rotor, and then a 3-phase inverter for an emulated load. Say if the load is being emulated by another induction motor, or if it's being emulated by a PMAC motor, you would need another inverter to do that. So that's the reason it has a 3-phase inverter. And the code generated is extremely efficient. Pretty much all of the functions were programmed in assembly to keep it extremely efficient, because the controller that we use is a little bit is a cheap controller to keep the cost down. So we had to make it super optimized to be able to get the best performance possible. So at the current rate, you could do vector control at a refresh rate of 0.1 millisecond, and it would still use only 1/3 of the processing capability. So you could do 3 permanent magnet vector control parallel at a refresh rate of 0.1 millisecond and still be within the processor capability. So here is a simple model that was developed using, in the last time we had a workshop, we had an hands-on demo for this laboratory back in DC, and where everybody got an opportunity to test this system out in real time, and they got to design their own DC motor speed control, which is shown here. So it's a simple controller. You have a speed reference and a speed feedback. The error is sent to a PA controller, and then you scale it by 1 by VDC, and then you do plus 0.5 times the duty and 0.5 minus the duty. You would get your duty signals for the top switch and the phase A leg and the phase B leg. So, and the participants were asked to design the PI controller values based on the videos that we watched. There was like 3-4 steps, and they input the D parameters and see the DC motor run in real time and look at the response and change the parameters, make it under damped, over damped, and all those simple models that were built. So this is the third experiment in our basic electric drives laboratory. The first experiment is a demo of the software. The second is the PWM operation of a H bridge. And then the third experiment is DC motor parameter estimation. And the fourth experiment is a DC motor closed loop speed controller design. And to make this model simple, we just use a speed controller. In the lab, we are required to design an additional inner loop current controller as well to be able to control the profile of the current. So this is a very simple system that can be designed using the software and run in real time to be able to control an actual DC motor. The same software can be used to simulate a much more complex system and run it in real time, as we shall see later in the slide. So this is the slide that I showed you earlier of an induction motor model. In the center, you have the induction motor, and the bottom, you have the DC motor. DC motor, which is used for emulation, so it's operating as a generator. And the DC motor is in current control mode, basically doing a torque control, a load torque control. And then the induction motor, we have the ABC to DQ, DQ to ABC transformation, all of those blocks here, which we will deal in detail tomorrow. And the reference to it would be the two current loops, one to control the magnetizing current, and the other to control the current which causes the torque, which produces the torque. And the input of the torque current loop would be your speed PI controller. And then if you want to extend it to position control, you can add one more PI loop, which would then feed into the speed PI controller. And as I mentioned earlier, each of these PI controller loops preferably needs to be at least 1/10 of the previous loop. So in our example, we are using the PWM switching frequency of 15 kilohertz. So the inner current loop, we would not set it any higher than 15,500 hertz, so 1.5 kilohertz. So for this experiment, we set it at 600 hertz, and then the outer speed loop was 1/10 of it, 60 hertz. And if we added a position loop, there would have been 1/10, 6 hertz. So so that was the model for doing the simulation. I'll run the simulation later in this video. Once we go to the hardware section, these are the we give 4 motors as part of the kit, the $2,700 kit. One induction motor, DC motor, two DC motor, one for loading, one for motor operation, and then one PMAC motor, and the whole assembly kit along with it. So the kit that you see here is to run the induction motor vector control. On the left, you have the DC generator, which is going to act as the emulated load, and it has an encoder on it to be able to measure the position and the speed signal. And then on the right, you have the induction motor. This is a 3-phase squirrel cage induction motor. And all of this is low voltage, all of it rated below 40 volts for lab safety reasons. And you could touch any terminal, short any terminal, and it will be extremely safe. Nothing bad could happen. It was designed with the extreme care so that no fault occurs in any of these systems, or no human hazard is caused because of any mistakes. So this is the hardware kit. This motor interfaces with, so the 3-phase of the inverter interfaces with the 3 phases of your 3 phases of the induction motor interfaces with the first 3-phase inverter, and then the DC motor connects to the other inverter where we use just the 2 phases. So here is the software in action. It loads pretty fast because the whole thing was written in native language. So this is the induction motor model that I showed you before. So let's jump right into running this model in real time. As you can see, you have the inverter model on the right, and then the induction motor and the DC motor. So once I go to real time, press the button, press run. Once the motor starts rotating, you would see the speed go to 100 radians per second at step time, and then settle. And all of the data that happens in real time would be logged back into the computer so that you can see them in the software live as the motor is rotating. So as you see, the speed started at 0, and then it steps to 100 radians per second. And we have a small load at 3 seconds where you can see a minor dip in the speed. I think there should be another bigger image of this where you can see it much more clearly. But as you can see, the model can, the same model that will be showing the simulation as well, can be run in real time. And then the results would be acquired by the hardware, the software, and displayed to you in real time as well. And it does not require any additional component for data logging or anything. So yeah, here's the bigger maximized version of the same graph. So as you can see at 1 second, we step the reference speed and the motor kind of has a under-damped response and settles down at 100 radians per second. And at 3 seconds, we had a torque load using the DC motor to emulate a load condition, a step load condition. And you can see the speed dip just a little bit before it recovers pretty rapidly and settles down. So we can design a controller which is a little bit worse in performance, and you can see like a bigger dip in the speed in that case. And the part of the one of the exercises in the lab experiment is to play around with tune the KPKI values for different phase margin and bandwidth, and see if the response becomes worse or better, and draw conclusions on the reasons as to why the response is different. So that was the speed response, and then you can also plot the torque response. So we're not exactly measuring the torque using a torque sensor because it's quite expensive. So what we do is the green is the DC motor torque, which is the load torque, and that is estimated by just multiplying KT by the current that we measure. And then the red is the induction motor torque, and that we get from the estimator motor model rather than measuring it using a torque sensor. And there is a discrepancy between the load torque and the actual the induction motor torque, and the reason will become obvious a little bit later. So this is the scope of your IDIQ currents. Again, don't worry about what IDIQ and VDVQ are. We will be going in detail over these. I just wanted to give you like a brief introduction to what the values would be looking like. So when we did the V by F control of an induction motor, when we looked at the currents, those were all sinusoidal currents. But once you go into DQ frame, these currents, if you select the DQ frame to rotate at synchronous speed, these current would end up being DC components in steady state. And the theory behind it, we'll go over it in detail tomorrow. But as you can see, these currents are logged in the small scope as well. So these are not actual currents in the motor. These are computed currents. So the actual currents are three-phase ABC currents, sinusoidal currents. And then the model has ABC to DQ transformation, which converts it to these DC values that you see and displays them on the scope. So if we were to just observe these values on a regular DSO or a regular oscilloscope, we wouldn't be able to do this without adding some mathematical function, time-consuming function, which are not available in a cheap scope. So as I mentioned earlier, the same model can be used to run both simulation and hardware. So what I'm showing you here is the simulation results and overlapping it with the results from the hardware run. So let me play that again. Here we go. So what we can do is compare whatever we got in our simulation with whatever we got using real-time modeling. So here I go. Okay, so I bring it out of hardware mode, run it in simulation, and once the simulation is run, so this result is the result of the speed waveform in simulation, and this is the result in hardware. So if you can see how closely the results match, and if the results don't match, you can figure out by debugging what's the difference between the actual motor model, the motor model in simulation, where was it the actual model. So if some parameter is different, then the results would be different. Or if you hadn't accounted for the power processing unit saturating at certain voltage, then the result would be different between what you would get in real time versus what you would get in hardware. So you could do all those forms of comparison and see how well your model reflects what it is in reality. So again, this is the, so if you look at this is the estimated torque versus the induction motor torque versus the DC motor torque. So when you saw it in simulation mode where they didn't have all these noise waveform on top of it, but the simulated, the estimated, the induction motor and the DC motor torque were exactly same. That was because in our simulation model, we didn't have a frictional model of the mechanical system, but in real time, there is going to be some viscous friction, which means that your induction motor is going to require more torque than it is actually being loaded by the DC generator, because it needs to account for the losses, the viscous friction torque as well, in addition to the DC motor load torque. So these kind of comparisons can be done between real time and simulation, and this is one of the questions in the Advanced Electric Drives Laboratory, where the students are required to log these data and then reason as to why there is a discrepancy between the simulation and the hardware results. And similarly, you have here the results of the IDIQ currents versus the real versus simulation, as well as the VDVQ voltages. So you can see they also match pretty closely. The ID currents in simulation in real time match pretty much. The IQ currents, again, there is a discrepancy because the IQ current is needed to compensate for the frictional element, which is not required by the ID component, because the IQ component supplies the torque requirements. So that was the lab for electric drives, both the basic and the advanced. And in addition to that hardware, we have a general purpose controller as well. So in the previous hardware that you saw, it had an onboard controller as well as all the power electronics on it required for 40 volts operation of these motors. We created an independent standalone controller board as well, which had an onboard FPGA on it. The FPGA can be programmed from Xilinx, and the DSP can be directly programmed from this Workbench software without any C programming. And we use this in all of our research projects, where we have requirements more than just controlling a simple 2-level inverter. So this hardware, we used it for controlling a multi-level matrix converter, for controlling a wind emulator, for controlling a solar PV panel emulator. So all of those projects, we use this particular hardware, a general purpose hardware, which has 64 PWMs and GPIOs and 16 ADC blocks and 2 speed sensors, all of it on the single board. And it can again be programmed directly from the same Workbench simulation software by just model drag and drop blocks. As I mentioned, yep, it's a general purpose. And again, this one also has an onboard data programmer as well as data logger. Again, the data logger is for low-speed data logging, like if you want to measure IDIQ currents or VDVQ, or you want to measure the speed position. So if it's anything within requiring a less than 100 Hertz refresh rate, you would be able to log with this. But if you want to look at the switching signal, you definitely have to go for a scope, because the computer cannot process that much amount of data. And again, the FPGA to be programmed does not require any JTAG cable or anything. The same USB cable that programs the DSP would automatically bypass and program the FPGA as well. So this can be used, the controller is not limited to use in just this electric drives alone. It can be used in any number of projects, as long as you use the controllers that we support, put it on any hardware, and that hardware should be directly controllable from the Workbench software. So it can be extended to any real-time controller. You could use it on a quadcopter, you could use it on a electric vehicle, you could use it on any real-time control requirements. You have the power electronics that you made and add this controller on it, and it should be programmable model based from the Workbench simulation software. And again, as I mentioned before, the software is completely free to download and use by any individual users or academic users. So that's the end of this presentation. And if you have any questions, you can email either myself or Professor Mohan at our UMN email ID. And you could also visit the website, which is cyamble.com, and you should be able to find all the resources. And if you have any questions when you're browsing the website, do shoot us your query and we'll get back to you right away. And if you want to browse through the laboratories, you can go to resources, go to CUSP laboratory. And right now we just have the electric drives laboratory for both basic and advanced. We do plan on adding power electronics as well as other labs there to this list, hopefully by next year. But yeah, this lab is currently available. So you could go through the manual. You could do just the simulation alone if you don't have the hardware right now. So for instance, if you go to switched mode DC-DC converter, you can just do the simulation to see the results. So let me, sorry. Yeah, let me go back to that. Sorry, I was in the presentation sharing. So yeah, this is the website. You can go to https://cyamble.com. And if you have a query, you can just go to the contact page and shoot us a query and we'll get back to you. And to go to the lab, CUSP labs, you can go to the resources, and here you'll have the basic drives laboratory. Again, we'll post a link to this on CUSP soon. You should be able to come here to that link as well. And you have all the experiments available for the basic drives lab, as well as the advanced electric drives lab, step-by-step instruction on how to proceed. And if you have the hardware, which can, so if you want to download the software, you can go to products and download the software. And anybody can download it. All you have to do is click download, and there is no requirement, no restriction. You just got to register, and the registration is free, and you should be able to download it. And if you want the hardware, you can purchase the hardware as well here in this link. So this kit has all the requirements that you need. It has the inverter, and it has all the 4 motors included within the kit. So, and yeah, so if you have the hardware, you can do the hardware part of the lab. And if you don't have the hardware, you can do the simulation part of the lab alone. So if I go to Workbench. So once you download the software, you should be able to access all the files that we have pre-developed for both the simulation and the hardware. So if you go to Explorer window, you can go to download project. It just downloads the project from the server. So let me just show a simulation project of experiment 2. If you look at the experiment 2 of basic drive, it's switch mode DC-DC converter, where we show the simulation of a switch mode DC-DC converter. So you can download the simulation project, and if you run the simulation, you can see the response of the 2 switches. So the A phase leg and the B phase leg. So basically turning on and off, and they should be phase shifted by 180 degrees. And you can kind of play around and change the duty. So right now it's at 5 volt. We are generating out of 40 volts possible. So let's go all the way to say 35 volts and then simulate the same. And you can see the voltage would be much higher. The duty cycle of the A phase would be higher and the B would be lower, making a net higher DC voltage. So if you can look at all the simulation experiments, again, you can just download them from this server. And tomorrow we'll be looking at the vector control full experiment, developing the model and stuff. So that is this experiment. Again, you go to the, minimize this. If you go to server, and instead of going to basic, go to the advanced electric drives, and you have all these 7 experiments. And the manual for it, you should be able to find the manual here in this link. So if you go to the help link, click on the help link, it'll take you to Cyamble resources pages where you can go to advanced electric drives, and you should have the full manual on how to proceed and do this experiment, both simulation and the hardware part of it. So you can run the simulation, and you can see the results and kind of play around with the parameters. And if you do have time, I would encourage you to take a look at this today before we meet tomorrow for the DQ modeling and stuff. Just play around so that you get a little bit familiar with modeling using the software. And if you have the hardware unit with you, you can just go to the hardware mode, connect the USB to the hardware and the motors, and press run. It should program it right away and run the motor. I don't have an hardware linked right now, so it'll throw an error. But those of you who have an hardware can link it up and run the hardware as well. So with that, I would like to conclude our first day session. And if you have any questions, I'll hang around for another 5 to 10 minutes. Just send your questions in the chat and I'll get back to you right away. And if you don't, have a good day. And let's all meet tomorrow again at 8:30. And before I forget, if you want to, we started off with permanent magnet AC motor in this today's morning session. Assuming that all of you who participated are familiar with DC motor modeling and DC motor control. If you aren't, you can go and take a look at these resources available on CUSP website. So if you go to cusp.com, cusp.umn.edu, sorry, and go to the basic machines and drives, and if you go to course videos, you should also definitely take a look at the course slides as well. The slides used in the videos were using these slides, so you can download these slides for the advanced drive if you want to follow along tomorrow. And you can also take a look at the lab. We still haven't posted our new lab on this website, this Cyamble lab. This is our old lab using DSpace. If you're interested, you could take a look at that lab as well. And yeah, so for the course video, you go to course videos in CUSP, basic electric drives, and you go to the drives link here, and you should be able to find all the videos. So the initial first 14 videos are about DC motor and their control. So those of you who are not very familiar with DC motor control, we would highly recommend you take a look at this, because everything that we are going to be doing tomorrow, all the vector control of induction motor and permanent magnet motor, is to emulate the performance of a DC motor. You have the constant speed response irrespective of how much you load the motor. So that's the whole idea of going to vector control. So it would be nice if you had an understanding of the DC motor as well. So that will be all, and have a good rest of your day. And if you have any questions, let me know. Thank you. Bye-bye.
Okay, so they are seeing me here.
Hmm.
Okay, so I can double click on this.
Hmm.
Okay, and
Hmm.
close this.
Hmm.
Okay, hello everybody. So we got done a bit early, but it'll be nice to kind of have a summary of what was covered today. And rather than go through it again, what is done here is I have a set of slides that you can look through. We'll upload them right away, and they kind of summarizes whatever we have done. So, if you have the time before getting together tomorrow morning, if you can look through that, it'll be very helpful, because then tomorrow we start on actual vector control of drives. And but we need to know what these machines do in steady state, and that's what we covered today. So with that, let's call it a day, and let's meet tomorrow. So thank you very much. Bye-bye. So if you could just say that